Space Shuttle Program Manager Wayne Hale to my right, and to his right is International Space Station Program Deputy Manager Kirk Shireman. Both will have opening comments, and then as usual we'll throw it open for questions. And with that, I'll turn it over to Wayne.
Well, thank you, Kyle. Good morning, everybody. It's good to see you. Feels like I've been up on the stage talking with you folks quite a bit lately, so you'll be pleased to know that you get to talk to the folks that really count a little bit later today, the crew that get to really ride the rocket, the real heroes of all of this, the folks that have been planning this mission and in charge with executing it, the flight directors representing all the flight teams, and all the people that have prepared this flight vehicle for this historic flight. The Orbiter Project Manager, Steve Polis, and the External Tank Project Manager, John Chapman, will be representing all those thousands of folks that have worked so hard to get Discovery back on the launch pad and ready to go again. But I think we got a little video, and I want to have folks roll that first, showing some of the processing. As you know, putting all the pieces together is a big part of the job. And these shots were taken over the last couple of weeks down at the Kennedy Space Center. It's been a big job to get the external tank ready. You can see the opening where we replaced the engine cutoff sensors at the very bottom of the tank. We moved the tank into the transfer aisle there to close that thermal protection system on the bottom of the tank out, and then like magic, you'll see here in just a second, it's all patched up and ready to go with new thermal protection system. And then we mated the external tank to the solid rocket boosters who are waiting for us on the mobile launch platform. All these shots are just tremendous, and when you're down at the Kennedy Space Center and talk to the folks who get to do this work or get to observe any of these operations, you get a feel for how really complicated and precise the system is. Here's the orbiter. We've done a lot of work on the orbiter, looking at a number of things. We replaced all the windows. We replaced about a third of the gap fillers. There were 15,000 of those guys, and we put in about the front third are all new installation to keep them from coming out. We not only have the boom for inspection with improved camera this time, but we have done a tremendous amount of work in Discovery in all areas, trying to make sure that this 20-year-old spaceship is ready to go fly. Rollout from the orbiter processing facility to the VAB was a great day for us. We're pleased that this very long time of preparation was behind us. We have replaced many components, evaluated a lot of structure, and are ready to go into what I think will be a rapid succession of flights over the next few months. Into the VAB, where we hoist Discovery up and over the bar into the integration cell, where we put the orbiter on the external tank, bolted on very carefully, and here we are rolling out to the launch pad. Another glorious day. Wonderful infrastructure we have at the Kennedy Space Center, which I think will serve not only the shuttle program as it has the Apollo program, but future programs as well. Out to the launch pad. The guys are really proud of these shots. These are good pictures. It's very inspiring to see the vehicle on the launch pad and the people that prepare it and participate all around the agency can take a great deal of pride in their work. So that's one of the necessary conditions to get to flight, is get the hardware together and out on the launch pad. Another necessary condition is to conduct the reviews of all the work. That's one thing that's been going on, will continue to go on. Yesterday down in New Orleans at the Michoud Assembly Facility, we had the design certification review for the external tank. And as you recall, we have made the largest aerodynamic change to this vehicle that has been made since we started flying 25 years ago. Removal of what we call the PAL ramp, the protuberance airload ramp, a piece of foam, actually two pieces of foam comprising almost 34 pounds of foam were removed from the outside of the external tank, and we had to verify that the components, the metal components that were protected from the aerodynamic flow by this ramp were still capable of withstanding those loads. We put together an intense campaign of wind tunnel tests, computational fluid dynamic runs, and other calculations to provide updated forcing environments for the structural analysts. The structural analysts have done thousands of calculations in the last 2.5 months, and we're able to report yesterday that in all areas they can show that we meet the required factor of safety, and we are safe to fly structurally without that those two large pieces of foam on the outside of the tank. This is something that probably would not have been possible in the early 80s. We have much more sophisticated techniques in the wind tunnels. We certainly have tremendously better computational facilities in the supercomputers and the aerodynamic codes that are used to compute these forces. And we can say with tremendous certainty today that we are structurally sound to fly without those two wind deflectors that were put on shortly before STS-1 because of uncertainties in the aerodynamic characteristics of the vehicle. In addition to that, we did review the other changes that we've made to the external tank. Most of those were focused on changes to the foam application. It seems like we're spending a lot of time with foam still. I'm here to tell you that we still have areas that we need to improve on foam retention on the external tank, and over the course of the program, the next 16 or so or more flights that we're going to fly, we will continuously improve foam applications and retention of foam on the outside of the tank. We certainly believe we have sufficient engineering evidence to show that we should not lose large pieces of foam off this tank the next time we fly. We will lose small pieces of foam, guaranteed. We have new cameras, and you'll see some of those pieces of foam come off. And some of these pieces do, under certain circumstances, could pose a hazard to the orbiter, and so that we know we have work ahead of us to continue to remove those hazards over time with each successive tank. In addition to that, we'll be going to the Kennedy Space Center on the 16th for the flight readiness review, where we're going to review all of the areas of the Space Shuttle program, the engines, the solid rocket motors, the ground operations, the flight operations, search and rescue, medical, crew operations, everything to make sure that all of those parts that are necessary to have a safe and successful flight are completely done. So reviews continue almost without end, it seems, but hopefully we'll get to the flight readiness review and mark a big milestone off. The third thing that is necessary for flight, of course, is the engineering testing. Engineering testing, some of which I've described in earlier briefings, will continue. We have a number of tests in a number of areas, everything from some of our metal balls flex hoses that we continue to worry about, some of our electronics, which is now getting a little long in the tooth. We continue to do a number of engineering tests to ensure that we're safe to fly. So we do engineering tests all the time, everything from piece parts up through main engine firings at the Stennis Space Center. And those will continue and help us reliably demonstrate good safety. And lastly, of course, it all comes down to people. And it has been my observation as I travel around the agency and talk to both the civil servants and the contractors at the various locations. We have the most dedicated and enthusiastic workforce imaginable. It is a pure pleasure to work with folks that are so dedicated and are working so hard to ensure that the nation's space program will be successful as we move out, not only to service the International Space Station, but also to be the next step on the vision for space exploration, where we'll be working toward going back to the moon and onto Mars. And with that, I'll turn it over to Kurt.
Okay, thanks very much, Wayne. And this is certainly an exciting time for the International Space Station program. We're very much looking forward to ULF 1.1, STS-121 returning to the International Space Station. So to start off, I'd like to talk to you a little bit about some of the activities that have been going on orbit during this Expedition 13, and I have a short video here I'd like to show you. So let's go ahead and roll the video. This video starts off with the 12th Soyuz arriving with Expedition 13 on April 1st of this year. And there's the Expedition 12, Bill MacArthur and Valery Tokarev with cosmonaut guest Marcus Pontus there. Jeff Williams here is replacing a remote power switch here, one of his first activities on board the International Space Station. Here, Pavel Vinogradov is preparing for the arrival of the 21st Progress. He's sitting at a telerobotic operators panel. And here you can see the Progress arriving. This arrived on April 26th of the year and was launched on April 24th. One of the beauties of having a new Progress is the crew gets some fresh fruits. And here you can see Jeff Williams enjoying an orange off the new Progress. The crew also has a lot of cargo to unload, so here Jeff is busy unloading the cargo from the Progress. And some of the cargo that came up is food containers. Here you can see the food containers stored in Node 1. The red containers are the Russian food containers, and the blue contain U.S. food. So here Jeff is storing some cargo in the airlock. In fact, you can see him there next to a U.S. spacesuit, an EMU. We take the cargo from Progresses and from a shuttle and store it all over the space station. We try to use every spare place for cargo. Here, Jeff exercises an important thing. So one of the ways the crew exercises is on the cycler exercise device, the Cevis, and also on the treadmill here in the service module. So you see Jeff out for his daily jog in the service module. Another important activity that the Expedition 13 crew has excelled at is Earth observation. Here you see Jeff Williams preparing for a session at the U.S. lab window. Jeff's already taken over 23,000 photos during his stay on orbit. He's on track to be the second most prolific Earth observer since we've had the space station. One of the research activities that have gone on during this expedition is the PFMI, Pore Formation Mobility Investigation, and Jeff Williams is conducting that in a microgravity science glove box. And here's an example of some of the data that's been provided to the principal investigators here on the Earth. Another important activity that's gone on during this flight, of course, was preparation for a Russian EVA. Here, Jeff is removing the Canadian Arm 2 in preparation for viewing of the EVA. Suggests that the robotic workstation here, positioning the arm in the correct place for the EVA. And one of the neat experiments we performed during this expedition is an experiment called Spheres, which is synchronized position, hold, engagement, reorientation satellite, and it's an independent free flyer inside the module. And lastly, you can see the crew outside on a spacewalk from last week. They used the Russian Strela, which is a boom, to help accomplish those tasks, and here they're maneuvering into position to translate to the U.S. segment. And finally, you see here the crew maneuvering onto the U.S. segment to replace this Canadian camera, which is what they're doing right here on the U.S. segment. So it truly was an international EVA. It was conducted in the Russian spacesuits out of the Russian airlock. They performed some Russian tasks, and then they translated to the U.S. segment, and then replaced a Canadian camera. Very much an international spacewalk. Let's see. As you probably know, we have a very busy year planned from the International Space Station program. If I could show you the first still image, this is our program plan for the year. For the remainder of the year, it actually includes from March through December. You can see that we still have 3 shuttle flights for the remainder of the year planned. We have 3 Progress flights and 1 Soyuz flight. On the far right column, you see we had 2 EVAs, 2 stage EVAs planned. The first Russian EVA-16 was conducted last week, and we have a U.S. EVA number 5 planned for late July, early August of this year. I'd like to focus a little bit on what STS-121 means to the ISS. The shuttle will be bringing quite a bit of cargo to the International Space Station, in addition to some important racks for the International Space Station. The first is the Melfi -80 laboratory freezer, and if I could have still image 131 up. Here is the Melfi with some technicians working on it. This is provided by the European Space Agency, and this will help in life sciences, human research. If I could have the next slide, 132. This is the U.S. oxygen generation system. This rack is actually the first step in allowing the International Space Station to achieve a crew of 6. If I can go to the next still, 133. This just to give you an idea of how complicated this rack is. This is half of the rack open, and the next image, 134, is the other half. This rack will be installed on orbit. There's quite a significant amount of work that must be done to make the ISS ready to support this rack, both in terms of the lab and actually it takes a spacewalk as well. So it'll be several months before this rack is activated. But it's important to get it on board the ISS and begin that work. Still image 135 shows the pump module. This is launched on the outside on the ICC, the Integrated Cargo Carrier. This will be moved from the shuttle onto the external stowage platform on the ISS during EVA number 2 in the upcoming flight. The next still image, number 136, shows the TUS reels, trailing umbilical system. You've probably heard a lot about this guy. You can see the technicians on the bottom, so it gives you an idea of the feel for how large this is. It's about the size of a grand piano. And this is important to allow redundant power data and video to the MBS, the mobile transporter, which will allow the ISS to continue its assembly, starting with the 12A STS-115. Let's see. The ISS hardware has been processed a lot at Kennedy Space Center, and I'd like to show you a little video of some of that processing at Kennedy Space Center. Here the crew is looking at a thermal blanket, actually investigating a thermal blanket that was manufactured to support the TUS reel. So they're reviewing it here, and they're actually installing it on a mock-up to make sure it fits and works the way they expect it to in space. The next, the crew is inside the MPLM Leonardo here in its fully flight configuration, looking at the cargo and how it's stowed and how it's labeled inside the module, and making sure they understand exactly how it's going to be, how it looks. Here the crew is inspecting the pump module. The photo I just showed you a minute ago, that's Peter Sellers, who'll be actually performing the EVA task to move it over to the external storage platform. And here they are again on the ICC, looking at the TUS reel. Now we're preparing to all the ISS cargo to go out to the pad. So this is the carrier, cross-bay carrier LMC, in the aft of the payload bay, being loaded into the canister. The canister is that device on the right. Here the crew, the technicians are inside the canister, and that's the ICC and the pump module that you're looking at. Yeah, this canister is an analog of the payload bay and is used to take the cargo out so that it's stowed into the payload bay. Here the technicians are lifting the MPLM Leonardo up out of its queue and carrying it over to the canister and inserting it into the canister. And finally here the canister is making its way. You can see they've rotated it vertical, and it's making its way out to the launch pad. As you can see here, the cargo went out based on the optimization of the processing flow out at the pad, went out to the pad a few days prior to the shuttle arrival. So the hardware is now out at the pad. It's actually been safely installed into the shuttle payload bay, and like I said, the space station program is very much looking forward to this flight and having the space shuttle on board the ISS and preparing the ISS for its continued assembly. I'd like to leave you with the last image, which is still number 138. One of the big objectives of this flight from a space station perspective is to go back to its intended crew size of 3. So this flight will mark the return of having the full complement of crew when Thomas Ryder, shown here in the far left, arrives and is left on board during this flight. That's all I have at this point, so I'd like to turn it back to Kyle.
Okay.
Great. Well, we'll take questions now, and obviously we've got a lot of folks here and at other centers. So try to limit it to one question, and for the audience out there, give your name and affiliation when Royce gives you the microphone. For his ease here, while Royce is there, let's work right in that corner and start with Mark.
Oh, thank you. I'm Mark Carreau from the Houston Chronicle. And my question's for Wayne Hale. Could you sort of give us a big picture in-game view from your standpoint of what's really happening here? It seems like this is a test mission, the second test mission, but it's also sort of the start to a sprint to the finish line for the shuttle to finish the station. And how important is it that this flight leads to the next, and what kind of pacing do you see through 2010?
Thanks, Mark. That's a really excellent question. We really are wrapping up what we think is our second of 2 test flights to demonstrate that we have improved the things that led to the Columbia accident. So we are expecting that we will be able to demonstrate that. And it is also the start, as we said, of the assembly process. We have 16 or so flights to complete over the next 4 years. That is not a tremendously hurried pace looking at the history of the shuttle program. There is time for us to stop or pause and work on problems for a little while. But certainly we would like to have a good flight where we didn't have any major problems and allowed us to turn right around and demonstrate we could fly again in August. It's going to be a real tight squeeze to get to that August 28th launch date. Atlantis is in the orbiter processing facility and getting ready to come out. The external tank is on a barge headed for the Kennedy Space Center, going to arrive there tomorrow for the second flight. So all indications are that unless we run into significant difficulties, we'll be able to press on and launch in that late August, early September window. But it is not a sprint. You know, we have to take every flight in order and make sure that we are operating within the safety bounds that we feel are necessary for this very difficult and risky endeavor called spaceflight. We understand that you cannot let the schedule drive you to make stupid decisions, and we are going to take every mission in turn and make sure that we feel comfortable with flying it before we do. As I said before, looking at the previous periods when we have flown shuttles on a regular basis, flying this number of flights in the amount of time that we have ahead of us before the 2010 retirement date of the shuttle is not a stretch. We should have sufficient time to allow ourselves to encounter what I would call the normal little difficulties that you encounter when you're flying in space and deal with them. So from the big picture standpoint, I think we're in good shape. Obviously, we'd like to see good results out of STS-121, but if we have some things that we uncover, and no doubt we will deal with them in their time.
Alan Boyle with MSNBC. I wanted to ask about the Hubble Space Telescope and whether there are already preparations being made. I realize you want to get through this first test flight first, but there may be some things, for example, crew assignment, that you're already doing to prepare for that eventuality of servicing the Hubble.
You know, there are some long lead items that are being prepared based on the assumption that we will be authorized to do a Hubble servicing mission. The authorization to do that mission has not yet been given, and I think it is dependent on how well we demonstrate our success in the next flight or two. Obviously, everybody would like to go back and service the Hubble again, but that is a decision that's ahead of us, and crew assignments are still up in the air, I think, for that.
Let's get Kelly and then work around.
Kelly Young with New Scientist for Mr. Shireman. Can you give us a brief rundown of what else is required for you to go to a crew of 6 and when that's estimated to happen?
Sure. First of all, we have to have oxygen capability, which this oxygen generation system is an important step. The Electron that's on orbit can support a crew of 4, so it's the 3 normal crew members plus a little margin. The OGS that we have would be able to support the remainder crew, actually slightly larger than a crew of 6. So that's important to have it activated. We have to have habitability enhancements. We have to have a place for the additional crew members to sleep. We have to have additional a bathroom basically on board to support the crew, and we have to have, of course, additional cargoes on board. So we have to have the additional supplies that crew members would have to have. Well, the plan is, and we'd like to have additional habitable volume. So as you know, we're planning on launching Node 2 next year, and the Columbus module manufactured in Europe, and the Japanese experiment module, the GEM, manufactured in Japan. All those things will allow additional habitable volume, and finally Node 3 on the ISS. All those things will be up on orbit, and we expect to go to a crew of 3 in 2009. I'm sorry, crew of 6. I said that wrong. We'll be able to go to crew of 6 in 2009.
Mike Cavish with the Orlando Sentinel for Wayne. You mentioned a minute ago that flying in August would be a real tight squeeze, and I wanted to ask you for a little more detail about that. If Discovery launches, say, even a week late because of weather or whatever, by my estimate, and correct me if I'm wrong, you would have about 3 weeks between landing and the FRR for the next flight. And given the fact that it took 2.5 years to fly after 107, and it's taken a year to fly now after the last mission, how realistic is it to think that you guys can turn around that fast? And what will you not do in between this mission and the next one that you have been doing between the last ones?
My observation on this is the long pole is being able to investigate whatever anomalous things happen in flight and get comfortable with them. You know, we always have funnies. We always have little problems. We label them in-flight anomalies. If it was something that wasn't normal and it happened in flight, it's an in-flight anomaly. And before you go fly again, you'd like to understand whether it was serious, whether it was trivial, whether it's something that you absolutely have to fix, whether it's something that needs a long-term redesign but is okay to fly with for a few flights. Whether or not you understand it is a big deal. We have gotten into the mode over the last several years of taking a tremendous amount of time and throwing a tremendous amount of effort at every engineering problem that we've got. And so the question is, can we streamline our processes so that we can thoroughly understand what happened? Because I expect we will come out of the flight with several dozen in-flight anomalies, things that need to be investigated and determined whether they're significant or not, and decide that before we go fly again. And you're correct, it is a short amount of time, and it'll be a little bit of a shift from what we've been doing. We have been laying management plans and engineering plans together to be ready to go do that. Clearly that is the long pole. I don't think the vehicle processing, turning Discovery around, those are not the long poles here. It is clearly the engineering resolution. Will we have enough time to take enough care to understand how significant whatever minor or major issues come out of STS-121, and then learn how to do that on a regular basis again. Before Columbia, we had this activity which was really jocularly called the orbiter scramble, in which the orbiter, which has the most complexity, the most number of parts, 2 million parts in that space shuttle orbiter, always had 2, 3, 4, half a dozen issues, engineering things that people were not sure about. In many of these cases, they turned out to be not significant when they were studied, or there was a very easy remedy that could be applied, but it takes some time to study them and to understand. And the problem is, if there is something really significant that you need to stop and fix, you have to come to a certain place in your understanding before you can make that judgment. That, I think, is going to be the interesting path toward flying the second flight in that September window. The good news is, you know, we have almost 3 weeks, 2.5 weeks of window, and we can certainly use some of that. We'd rather not, but we can certainly use some of that if we need to allow the engineers more time. Again, when we look at the vehicle processing, getting the hardware there, putting it together, getting Atlantis ready, turning Discovery around to be ready to fly a rescue mission if required, those things I don't think are the pacing items. It's the engineering analysis, because I can tell you today we will have, you know, 12 to 100, I can't tell you how many, in-flight anomalies, which is nothing more than a squawk list that says we need to understand why these things didn't operate exactly as we thought they would. It's a standard thing for a space shuttle flight, but again, we have been in this period for the last several years where we had lots of time to do that. Now the time will be a little bit compressed.
Well, Bill Harwood, CBS for Wayne. I'm confused about the certification process of the tank. The 1.4 factor of safety that applies to wells and things like that. Can you maybe just walk me through what got certified, and when you say we've got a sufficient factor of safety, what is it? I mean, how do you quantify just how much you've got beyond worst case?
There were over 100 different piece parts on the tank, mostly brackets, structural items such as the cable tray, the pressurization lines that run on the outside of the tank that were affected aerodynamic with the aerodynamic forces that changed through the removal of the PAL ramp. After we got the aerodynamic forces, again coming out of the wind tunnel, computational fluid dynamics, other analysis, after we got the aero environment, we turned that over to the stress analysts, and they calculated in detail the maximum stress for every piece part, every bolt that's affected, and they demonstrated conclusively that we met what we call our 1.4 factor safety. So on the worst case load, on the weakest part, we have 140% of the strength that you need to ensure that your structure holds together. And I've got to tell you, when we went to the design certification review, and again, this was the management review of the design certification, when the engineers came in and presented their discussion on the factors of safety and the margin that we in fact have in every area above that factor of safety, it was kind of I don't want to say disappointing, but it was the denouement was not very exciting because it was so cut and dry. There was no question. I mean, we struggled a little bit because we're managers and they're paying us to be there to ask questions of the engineers and poke a little bit and make sure they did their work thoroughly. But this is a standard process. Structural engineering, as opposed to maybe foam engineering, is a well understood process, and people do that all the time. And the tools are well understood, the processes are well understood, the calculations are straightforward, and it was just kind of unexciting. I was hoping for a little bit more drama, and they came in and presented the results, and it was all good. And we, like I said, asked a few questions, and it was all good. And time to sign the certification papers and go home.
Todd Halverson, Florida Today for Kirk Shireman. I'm wondering if you can discuss for us the importance of the EVA with the trailing umbilical system wheel assembly. Is that EVA required to be completed successfully prior to the resumption of station assembly? And are there other items beyond that that also need to be finished before you resume construction?
Right now, the mobile transporter, the device that's like a rail car that moves along the truss, it normally has redundant power, has two ways of getting power, data, and video to it. One of those cables was cut, the trailing umbilical system that provides one leg of that redundancy, so we're down one leg. We have rules in place that say we do not base the arm on the mobile transporter during that time, and we do not maneuver the mobile transporter. Those are flight rules, and we can violate them if we need to. We take them very seriously. And in fact, we plan to maneuver the mobile transporter during this flight with only one leg of redundancy, because we have to move it out of the way to help install the test reel, trailing umbilical system reel. So it's very important for us to restore full functionality before we continue assembly, and that's because to continue our assembly, we have to move the mobile transporter out on the truss, base the arm out there to actually install the next piece of truss. So that's the very important piece of this mission for us to return to full functionality. And of course, the other piece on this particular flight is returning to a full complement as it is today of 3 crew members. If you look at the number of hours, crew hours we have to accomplish all the work on space station, which is maintenance, assembly operations, and utilization, we have 2 people on board today. When you go to 3, that's basically a 50% increase in the amount of crew time available to perform those activities. So that's very important to us as well.
So let me take 2 more here and then go around the centers, and then I'll come back and catch some final questions. Irene and then Tracy.
Irene Potts with Reuters. I have 2 for Wayne. The first is, could you describe what it's going to look like if we're going to be able, if anything's going to be different during launch with any vibration or shaking on any of the structures that the power plant was previously protected, and what and if you also could say what the weakest link is. And the other question is about the overall thinking of this flight as far as determining whether the foam fixes are successful. Do you have a specific criteria as far as weight or size or quantity of foam that you need to be under a certain threshold to be able to feel that you could safely fly again in 3 to 4 weeks?
Oh, I wish you could have been with us yesterday. I thought about inviting somebody to come to the ECR because we had this huge discussion on exactly the top. Well, to your first question, Irene, vibration, additional vibration, no. You know, we saw, if you'll recall, on 114, the cameras from that looked down the big 17-inch diameter feed line. That feed line has some vibrations in it. We expect to see that again. No worse than what we saw before. That's within the design capability, and that's well understood. We don't expect to see, to the best of my understanding, any vibration or movement in the pressurization lines. They're stiff. They're under pressure, or nor the cable tray. What we will see that's different is we will have new cameras on the solid rocket boosters. There are additional cameras that have different views. I think we're going to talk about that a little bit later today. Those camera views are recorded on recording devices in the solid rocket boosters, and when we get those boosters back into Port Canaveral, about 3 or 4 days after launch, we'll get the tape out and we'll review the tape and release it, very similar to what we did last year, but we've got different views this year, and we will see different views of the tank during launch, looking up and looking down, and I expect that we will get some more views of some of these little popcorn pieces of foam that come off, anything bigger that might happen. To your second question about the foam, boy, we're spending a lot of time on foam these days. We have a document that lists for every area on the external tank what we expect our maximum release, our maximum debris size is. We had quite a bit of debate over that, and we are still learning about the physics of foam. It is not a well-understood material in the structural sense the way a metal is a well-understood, well-characterized material. But the things that cause foam to come off, we have an understanding, but it is not an in-depth understanding in many areas. In other words, we know some things happen, but we can't explain the physics of exactly why, and connecting those dots is something that we are continuing to do work on. So we look at what the historical evidence has been from previous tanks, mostly the photographic record. We look at what happened in the ground tests. We look at what happens analytically when you try to, think about the physics involved and do an analysis of what might come off. And when we have a huge discussion about which one of those is the most valid, and have we covered all the possibilities, and what are the largest sizes that might come off. And we've developed a table of all these applications up and down the tank of the sizes that might come off or have come off in the past. And then because we know that we haven't observed everything that might happen, you apply statistics to it, and when you apply statistics to it, that's a whole other discussion in itself, and increase the size, and we have what we call a limit. And in some cases, the limit doesn't mean that it's a bad thing if it comes off. It just means that we didn't understand the physics of release as well as we should have, and we have more work ahead of us. So in other areas, it is a bad thing, and we really don't want a piece any larger than that to come off. So we have these limits, and when we get the photography back after the flight, we will go over this photography in great detail, looking at, because that's the only way we know what came off the tank. We don't get the tank back. It's the only piece we don't get back. I really wish we could bring it back, but it's kind of hard. And do our best photographic analysis of what came off, and then if it's larger than what we expected, we'll call it an in-flight anomaly, and we will again discuss it. And some in-flight anomalies, as we talked about before, are just we need to understand better and make a judgment on that. Some in-flight anomalies are, hey, we really have got to go fix something. The STS-114 PAL ramp release is kind of the poster child for the second category. We lost a big piece, but we clearly didn't expect it. That's a stop and fix mandatory before the next flight. I hope we don't get any of those. We understand the physics of release a lot better this year than we did last year because of the work that's been done. So we do, yes, we have a list. We know what we expect, and we'll see if we get anything bigger than that. Hopefully it's all smaller and less frequent than is in our list.
Tracy.
Tracy Weston, USA Today. To follow up on film, what if you do see something bigger than you expected? What are the consequences for the shuttle program, do you think, if you have significant film debris or some other kind of debris strike on the vehicle?
Well, look, we are operating in a tough environment. We are operating at high speed and high energy environment, and there are not a lot of people that fly in these environments. Most of the expendable rockets that fly in a launch pattern similar to the shuttle, they don't care if stuff comes off the outside, and frankly, there haven't been a lot of study on it. So we're the only vehicle I know of that really cares about what comes off during the launch phase. And by the way, one of the goals of the next spaceflight vehicle that we're designing is to not be vulnerable in these ways. That's a safety improvement that we think is mandatory in the next generation of spaceflight vehicles. So, we are. I cannot tell you we are at the graduate level in understanding all of these phenomenon. We are definitely students now of flying polyurethane foam at supersonic speed, trying to understand what happens to it. We believe we have a good understanding, but I would be kidding you if I told you that we understand it as completely as we'd like to. We have a long way to go.
Okay, let's go to NASA headquarters for one question, and then the Kennedy Space Center.
Yes, thank you. This is Seth Bornstein of the Associated Press. Wayne, you talked about you have room in the schedule if you have some of the normal, unexpected events, some slippage room in the schedule. Can you explain? Obviously, you probably don't have room for another year down. Can you give us some quantification on how much room? And also, are you telling us that the 2010 deadline and the 16 flights and that calendar pressure has at play no effect? Hasn't come up in any of the management decisions? It has to have come up somehow, hasn't it?
Well, of course it has, Seth. I don't kid you. People talk about schedule. We have scheduling meetings all the time, and we talk about the manifest and how this is all going to lay out. The point is not that there isn't some schedule that doesn't cause you some, I don't use the word pressure, but it causes you some concern. I mean, everybody has got a schedule, whether it's getting up in the morning or when you have to turn your report into your editor. But the point is, we have a renewed commitment to not doing something stupid just for the sake of schedule. We really want to do a thorough job of understanding our problems, and we're going to deal with them. And as to how much quantitatively space we've got, we can fly 6, 7, 8 flights a year. We've demonstrated, I think, as many as 9 flights a year. So flying 4.5 ish an average flights a year is not something that I think is a great stretch. The real difference is going to be that we are going to pay a tremendous amount of attention to this experimental vehicle to make sure we understand what the problems are before we go fly again.
Let's go to the Kennedy Space Center in Florida for a couple of questions, please.
Stephen Stock with WESH out of Orlando, Channel 2 TV for Wayne. Yes, another question about the foam. I want to go back to Mike Cabbage's question and your response about these anomalies you have to fix. There remains divisions among even your safety engineers, including your top safety officer, about the fix for this foam, including the ice ramps. Why not fix those ice ramps before flying STS-121? And what is the implication for 115 and 116? Let's say you have these ice ramps, there's too much foam. I mean, you can't turn around 115 and fix it by then, can you?
Well, you know, we have had a very serious study on this. One of the things I think that was wrong before Columbia is we didn't pay enough attention to some of the problems we had, in particular foam problems, and I would be happy to report to you we pay a lot of attention to those problems today, and we're not making any decisions on an ad hoc or schedule-driven basis. We're taking a very hard engineering look at these things. And I've said before, and I'll say it again, you know, if we could go back 25, 30 years and change the design of the shuttle, the number one thing that I would say we needed to do was to not put our fragile heat shield in an area where debris can come off during the early first 3 minutes of flight and cause us catastrophic damage. I mean, that is if there was one critical thing that we could change, I wish we could change that. But it's the vehicle we got, and it's the only vehicle we're going to have for the next several years. So if we intend to be a spacefaring nation and put Americans into space on an American flag vehicle, it's going to be with the space shuttle. Our job is to make that as safe as we practically can. It's not going to be perfectly safe, and oh, by the way, the next space vehicle, which will be a lot safer, it will not be perfectly safe either because of the energies and heights and so forth that you're dealing with. So directly to the foam, we identified a critical problem out of STS-114 that we did not understand. The last shuttle flight lost a 1-pound piece of foam off the PAL ramp, and we said that is no good. We can't have that. We've got to get rid of the PAL ramps. Now, we knew the PAL ramps were a hazard, and we had a plan that over the course of about 2 years we were going to do a very orderly, systematic, and thorough job in removing the PAL ramps from the external tank. We accelerated that plan because we said that is job number one. And I'll go back and tell you again, that was the most hazardous piece of foam we had on the outside of the tank. We decided to fix it, and we accelerated that work, and then we said, what else can we look at on this tank? Now, there are over 300 manually applied areas of foam on the external tank. I don't know if you look at the tank, it's a big tank, and I don't know if you go back and look at those pictures we showed you before, and compare it to the people in those pictures, it's a huge tank. There is over 4,000 pounds of foam insulation on the outside of the tank, which we have to have because it's a little thin-walled aluminum skin and cryogenic fluids on the inside will form ice on the outside, and your cryogenic fluids will boil away on the inside if you don't insulate it. Got to insulate it. Now, we apply much of that foam, about 3/4 of that foam, robotically in a very controlled application. We really don't have problems with that foam coming off. It's the other quarter of the foam, which is applied manually with people with spray guns, and we've improved all those processes a lot, but it's still applied manually that we are concerned about. So we took 34 pounds of foam off the outside of the tank. Out of 4,000, it's not a great deal, but it was the largest area of risk we had. We said, well, what is our next area of risk? Everywhere those protuberances, which is the cable tray, the two pressurization lines on the outside of the tank, are attached to the metal structure, obviously you have metal to metal that's in contact with the cryogenic. Ice can form on those metal structures and they have to be insulated. Therefore we have 34 foam ice frost ramps on the outside of the vehicle, and you add up all of that foam together and it's about 35, 36 pounds of foam, roughly equivalent to the power ramps, but distributed in smaller dollops, if you want to think about it. Physically, it's a smaller structure of foam, so you physically can't lose as big a piece. And our historical evidence, and we look back, we think we've got really good photography of somewhere between 20 to 25% of all of the ice frost ramps that have ever flown. We look back and we have done a really good job, I think, of measuring the pieces that have come off in the past. And we've tried to replicate that on the ground test. But we know that pieces potentially can come off that could be harmful. So we have got to fix that. And I think we have a fix that's probably slated for the third or fourth tank. But we have to ensure, first do no harm, that our design is a good design. That design has got to go through tests and make sure that we don't pick up some unanticipated consequence and make things worse with a new design. But we have a strong team that is off working on it very hard. Mr. Steve Cash of the Marshall Space Flight Center is leading that team of redesigners. So we're left with what we know is a hazard that we need to fix. And by the way, once we get the ice frost ramps fixed, there are other areas in the tank that where we have foam that we're going to work on. The area in particular on the ice frost ramps, we think we could lose up to 0.2 of a pound of foam. Well, off Columbia, we lost 1.5 pounds, 1.6 pounds. Off the power ramp on STS-121, we lost 1 pound. We've eliminated both of those. The next largest piece we can lose, the biggest we've ever seen is 0.09, less than 1/10 of a pound, but we think statistically we might lose 0.2 of a pound, even though we've never seen that. So you're looking at smaller and smaller pieces of foam that, by the way, come off less and less frequently. When we're on a continuous improvement path, once we fix one, we're going to move to the next highest, the next largest area release, the next most frequent area release, and fix that. So it's a continuous improvement process. The question is, would you stand down to the end to get every one of those fixed? Well, that's a little extreme. The real question is, on this particular flight, why would we not stand down and fix all the ice frost ramps? And there's a couple of good reasons. One is we don't have a good design in hand today. That's in work. But secondly, there is a principle in flight test, and remember we are in a flight test on an experimental vehicle. It says when you have made a major aerodynamic change and you have studied it in the wind tunnel and you have studied it with the computer simulations and you think it's good to go fly with, you go fly with that one change, because all those wind tunnels and all that analysis and all those computer models are never quite as good as real life. You really need to go fly it and see whether it works like you think it was going to, and get that data before you proceed to change anything else. And it's that flight test principle that we're resting on here today. It is nice to say you ought to stand down and fix all your problems. If we adopted that philosophy, we would never fly. We think we have identified the most critical problem. We've fixed it. We need to go flight test it. We have additional sensors this time. We have additional cameras this time that will bring us back information on how well that worked. And once we feel comfortable that we have accommodated the power ramp removal successfully, we're going to move on to the ice frost ramp redesign. And that's the way it works in aircraft flight test engineering, and I think in spacecraft flight test engineering. This is an important point. I'm giving you a really long answer because we have had a huge amount of discussion, and we have taken this complete story, all the dissenting opinions, the full engineering story, all the way to the administrator. And that's the decision we've come to. And are we at risk? Absolutely, we're at risk. What's that great quotation John Young used to always say? If you're not a little scared when we launch the shuttle, you don't understand what's happening. Okay? And that's going to be true, by the way, after we fix all the foam on the external tank. There's plenty of other reasons to hold your breath. But it is a judgment call. There are always pros and cons. I wish that these decisions were nice and easy and black and white, but it doesn't seem to be our lot in life to get those kind of problems handed to us. We get all kinds of shades of gray, and you use your very best judgment and rely on your very best engineers, and then you go forward with what you think is best.
Hi, this is Mike Schneider with the Associated Press. Wayne, I had a kind of a general question for you. So many of the technical issues that you're dealing with were the same that you were dealing with last year at this time, and I was wondering if you could comment on the similarities between where you all are right now and where you were last year, and does any of this feel like deja vu all over again?
Well, it does. You know, I expect that as long as we fly the shuttle, we're going to be worried about structural corrosion. We're going to have to do corrosion inspections on the vehicle. We don't talk about that a lot in the press conferences, but that's an ongoing thing. You go park your airplane at the beach for a month every year and get salt spray on it, you're going to have to worry about corrosion. Wiring, we have had an ongoing concern with the Kapton insulated wiring in the space shuttle, and it's going to take a lot of vigilance and a lot of continued inspections and repairs as we get this 300 miles of wire in every orbiter to make sure that we don't have a frayed place where we could have a bad place in the insulation. We have a continuing saga with our old electronics. You know, the shuttle's like an old truck. You know, it was designed in the 70s. We had all this really, 70s vintage, state-of-the-art electronics, which is really old now. And you say, well, why don't you replace it? Well, that incurs a whole nother risk and a whole nother expense. But we keep making sure that our electronics is working as well as it should be, given its age. And so, yeah, it's just deja vu all over again in a lot of areas, and many of which we don't come here and talk about in press conferences. In terms of the foam, we are so much smarter this year than we were last year because of the tank that we took to the Kennedy Space Center and filled up twice with cryogenics and emptied, and then shipped back to the factory where we tore it apart. All the foam has been torn apart, examined in detail, dissected in detail, and that is the first time in the history of the shuttle program we've ever done that. You know, most of the parts we get back, we tear the engines down and look at every little seal and every little rotating component bearing in the engines, but you don't get the tank back. And this is as close as we've ever come to having a tank back, and we learned a huge amount from that tank. So we are far smarter today than we were a year ago. And we're going to continue to work on getting smarter for the future as well.
Okay, we're back here. Two final questions, this gentleman and then Kate.
Thanks. Tom Costello with NBC. Wayne, two quick questions for you. One is the disposition on what you finally determined was the problem with the sensors at the bottom of the external fuel tank that caused a delay in the launch last year for a good week to 10 days. And second of all, can you discuss at all the plans for EVA-3 if you're able to carry out EVA-3 and testing the repair techniques on the exterior of the shuttle?
Right, and I would kind of refer your second question to the flight directors, and they have really worked with this. I think we have a high probability of being able to pull off that third EVA. We're always going into flights with a plan that will allow us to do more if we are conservative with our energy and have enough electrons left to stay an extra day. And I have a pretty high degree of confidence we'll be able to pull that off and do those repair tests. But I'm going to refer you to their press conference for all those details. First question was, the sensor. Oh, good. Okay. You know, that's one where I feel much better. We built these little sensors, which are Apollo Saturn heritage sensors, for many years. We've identified a period in 1996. Now, you know, we pay a lot for parts in the space program, and sometimes the people on certain TV shows make jokes about how much we pay for parts. One of the things we pay for is rigorous testing and documentation. So here we are 10 years later, and we have all the build records on these little sensors we made 10 years ago. And we can go back and look at them. It turns out there was, I don't want to say a problem, but there was a situation in manufacturing these parts where we did not always get a good electrical connection between the sensor and the wire that goes out to the data system. We've identified a way to x-ray those parts and tell if we've got a good connection or if we've got a suspect connection. Without doing that x-ray, we think that there's a reasonable probability that we have a sensor that might fail on us. So what we have done now is we've gone off not only and acquired new sensors, new manufacturer sensors, but also screened a bunch of our old sensors that were on the shelf, and we've taken out all the ones that have this poor electrical connection. And we are in the process of going into tanks that have been built with these sensors and replacing all of these sensors with good, new, or screen sensors. So I'm pretty confident that we have got this problem behind us. We still have what we call a system level test that's looking at on a bench, not just the sensor, but all the cable harnesses and the electronic box. Again, a 1970 vintage electronic box that reads these sensors and tells us whether they're wet or dry, whether you're out of fuel or not. And that test is going to be going on over the next few months, and we may find something in the connectors or the wires or that electronic box that we also want to go fix. But I'm confident we're well on the way to putting those sensor problems behind us.
Kate, you're the final question.
Kate Tobin with CNN, and my question also relates, I guess, tangentially to Spacewalk 3 and the whole issue of TPS repair on orbit. If the spacewalk doesn't happen on STS-121, are there plans to reschedule it for 115? Are there any plans to do additional tile repair testing? And big picture, what's the thinking about on-orbit repair, especially as you're looking at maybe doing a Hubble servicing mission that would not go to the ISS?
You know, repairing the thermal protection system on orbit is a difficult situation. I mean, if you think about what the thermal protection system does, we fly back through the atmosphere and generate temperatures of 2,800, 3,000 degrees. You know, the temperature of the visible surface of the sun is only about 3,000 degrees. So you're literally flying, you know, through an ionized cloud that is that temperature at the surface of the sun. And you're flying through that for more than half an hour. And on the back side of your heat shield, your thermal protection system, is you've got aluminum, and you get aluminum above about 350 degrees and it begins to lose strength. So, you know, not much hotter than you bake your cake at, and you have to start worrying about the cake pan. The thermal protection system on the orbiter is a marvelous, marvelous invention. It weighs very little and it insulates incredibly well. And to say that we are going to go out on orbit and patch a hole in it that would be able to survive that environment, I mean, that is a huge technological challenge we've been working on for the last 4 years now. We have some capabilities. They, again, are not certified. They're not as completely wrung out as we like. They all have limitations. We would use them in an emergency. I think they provide a line of defense, but it's not something that you really want to count on. We are continuing to put money into further research and development of improvements to those capabilities. Again, we have 4 or 5, let me count them up in my head again, capabilities to repair the thermal protection system that we're carrying on every flight right now, and we would use them if we had to. However, we're going to continue to work on improving those. And so by the time we come around to a Hubble flight in another year or two, where you can't go to the International Space Station and hang out with your friends for another ride home, we really need to improve those repair capabilities, and we're continuing to work on that effort to repair them. Now, in terms of not doing the EVA on STS-121, I'm sure we will try to reschedule those objectives and probably future objectives on future EVAs. The real problem with that is we're back into the business of assembling the space station, and our EVA time becomes very precious. And when you start moving solar arrays around, like we're going to do on the next assembly flight, it's going to take all our attention and all our EVA time to get that done right. So shoehorning in some additional repair tests is going to be very difficult. That's why we designated these 2 flights as test flights, and we need to do as much as we can on the flight we flew last summer and this next upcoming one.
Okay, that's all the time for questions we have. You have anything else, Wayne?
Well, I just wanted to say, you know, we've talked an awful lot about this thing. You're going to hear about the hazard report that we're writing. We talked a little bit about the ice frost ramps. I want to clarify for you, we're writing a hazard report that is going to impress on upper level management, that's me and everybody above me, that ice frost ramps need to be worked on. So you're going to see a hazard report that says it's important before the end of the program that we deal with those ice frost ramps in particular. So don't be surprised when you see that. I think we may baseline that today. I did, in the last few days, happen to watch an interesting series of shows on TV, and I won't plug the channel, but talking about the 1950s and 60s and how we got into space and how challenging that was, and how people used to have their rockets blow up on the launch pad, and how few successes we really had in the early days. And I got to tell you, we're smarter now, but things really haven't changed a whole lot. Getting to Earth orbit is a hugely difficult problem, and even when you get there, there are many more risks. We have orbital debris, we have the extreme speeds and heat of re-entry, pressures and temperatures beyond everyday ordinary comprehension. It just is not the kind of thing that your conventional experience will give you a good judgment in. We are an inherently risky business. But we as a nation have always grown because we have been a pioneering country and explored the unknown. And that involves taking risks. What we're doing here today is maintaining our outpost in space. This is the only place in the frontier where there's a permanent human presence, and this is an important step. And so it's a risk worth taking. And I'm trying to remind all of my workforce, and I would remind you as well, that what we're doing on July 1st is not just carrying some food and water and a cable reel to the International Space Station. We are actually taking the next step on the road to Mars, and it takes a great deal of care and attention from everybody involved. We are really, truly involved in pioneering the space frontier, and I think it's important for us to remember that.
Okay, we got a quick turnaround for the next briefing. Up next, the mission overview, so sit tight. Thanks, gentlemen.
Good morning and welcome back to the NASA Johnson Space Center for the continuation of our pre-flight briefings for the STS-121 Space Shuttle mission, which is the Utilization and Logistics Flight 1.1 to the International Space Station. This is our mission overview, and to provide that and all the details of this mission, we have the lead flight directors with us today. The lead for the Space Shuttle is Tony Sacacci here to my right, and the lead for the Space Station is Rick LeBeau to his right. So we'll open up with comments from Tony and Rick first, and then take questions from around the NASA Center. Tony?
All right. Good morning, everyone. I hope all of you are as excited to be here as Rick and I are. That means we're getting close. See, Rick and I have been lead for 121 in the ULF 1.1 mission almost 3 years now in September. And during the first 2 years, we were always designated as the next mission, which no one really paid attention to. But despite that, we continued to charge ahead, overcame the various challenges, and with the help of our team, we've come up with a pretty good mission plan to execute. And of course, we're going to follow through with which STS-114 did and have a very successful mission. one of the things I had the benefit of doing is working STS-114 as the Orbit 2 shuttle flight director. So I was involved in the planning and, of course, execution of that flight, and all the lessons learned and valuable information that we came out of 114 we were able to use on 121. See, before I get started, and I know that Wayne had done this previous, we just wanted to thank all the folks that were involved in getting both the shuttle and the station ready for flight, applaud their hard work and sacrifices, and you know, you see the orbiter on pad 39B, it says it all. See, first thing, as tradition, we want to go ahead and introduce the STS-121 crew. You guys will have time to talk to them this afternoon, but we'll just give a quick introduction. Of course, from the left just is Stephanie Wilson. She's Mission Specialist 3. And we have Mike Fossum, Mission Specialist 1. And of course, CDR, Steve Lindsay. We have Pierce Sellers, who's Mission Specialist 4, and him and Mike are our spacewalkers for this flight. We have the pilot, Mark Kelly, next. And then we have Thomas Ryder, who will be the third station crew member we'll be bringing up, and Mission Specialist 2, Lisa Nowak. See, along with all the other duties as assigned, Lisa and Stephanie are our arm heavies for this flight, for both the station arm and on the shuttle arm. So like I said before, Piers and Mike will be our spacewalkers. See, the next I wanted to introduce the flight directors that will be supporting the 121 mission on the shuttle side. So if I can get the first one up, this is Steve Stitch. He'll be doing the ascent and entry portion of the mission. Next one, please. Of course, myself, younger a couple years ago. Next one, please. Norm Knight, he'll be supporting the Orbit 2. And if I can get the next one, Paul Dye, he'll be supporting the Orbit 3 flight control team. And Paul is the lead shuttle flight director for the next mission, 12A-115, coming up. So as far as the mission overview, our plan today is to give you an overview of all the activities we'll be doing for the 121 ULF 1.1 mission, and I'll present the shuttle side of the operations, and Rick will be presenting the station side of it. As we go through the mission overview, it'll probably look pretty familiar to you. STS-121, we're doing about 70% of the same activities as 114 did. And of course, we had minor lessons learned as we executed them on 114, and we've incorporated them into the 121 ULF 1.1 plan. I think there were some questions previously that Wade answered, but current mission duration is 12 days, and we have a very good chance of getting the 13th day, depending on when we launch and the available cryo at launch. The decision was made to go ahead and maximize the number of sequential launch opportunities, and that's where the 12-day mission came from. And with the 12-day, we have a pad hold capability of greater than 96 hours. So that's about 5 if you wanted to in-a-row launch attempts, if that's the way we want to go. Our major mission goals for this flight include completion of the return to flight objectives. In our flight, we're looking at evaluation of additional TPS inspection techniques, being the IR camera, and we have a new sensor on the OBS, orbital boom sensor system, which is the IDC. Evaluation of the OBSS as a TPS repair platform. We'll be doing that on EVA-1. And if we get the opportunity on EVA-3, we'll be doing RCC repair with NOAX. We also, another goal is to return the ISS to a 3-person permanent crew that Kurt had mentioned previously. There's been failures on the ISS side to the mobile servicing system, and on our EVA number 2, our plan is to get that back fully operational, because we need that to continue the assembly sequence starting with the next flight. Of course, we're bringing up multi-purpose logistics module Leonardo, and we have some critical supply transfers and returns that we need to complete. as with 114, the crew timeline is fully subscribed. There's zero white space for them. They're really busy, and they're going to be earning their pay this flight. Unlike 114, where we had 7 dedicated shuttle crew, we only have 6 for this flight because Tomas, once we get back, it's going to be done over the station side. It doesn't mean we're working the crew harder. It's just that we have to move things later in the flight to get it done. Let's start with the payload overview. See if you want to go ahead and roll that. Again, this is familiar to you as we go through here. First thing we'll see is the orbiter docking system. Okay. Next thing is the integrated cargo carrier. That has, we'll talk about what's on there, as the pump module and the TUS. Of course, the multi-purpose logistics module. And then on the lightweight MPAS, we call it, we have a tile sample box where the RCC samples are located. And Tomas Gonzalez will provide more details on that this afternoon during the EVA briefing. We have both the, of course, the orbiter boom sensor system and the remote manipulator on. So we'll have some photos here of the cargo carrier showing both the TUS, wheel assembly, the pump module that will be used, one of the spares that are required for the 12A.1 mission. Got ahead of myself there. And then you'll notice underneath the ICC, shortly we have 2 fixed grapple bars, and one will be used to go ahead and move the pump module from the ICC to ESP2, and the other one we're going to attempt stow, if we have time, over on one of the ammonia tanks. Okay, let's see, starting off with Flight Day 1, of course that consists of both the ascent and post-insertion activities. Besides getting the orbiter ready for on-orbit ops, the crew has a number 1 priority task to get the computer network set up on board so we can get down the imagery data and the wing leading edge data on the orbiter. And although we don't anticipate any large foam shedding or debris impact, it's just important to get this data down as quickly as possible so we can get the folks to start reviewing it and evaluating to determine if anything unexpected has been seen. See, the crew will also be doing water spray boiler DTO, same as they did on 114, and basically there's some antifreeze that we've added to APU3, and we're making sure that antifreeze will allow us to restart the APUs earlier in the mission, just in case we had a contingency first day PLS that we had to attempt. See, another activity we'll be doing on Flight Day 1 is we'll be positioning the RMS in a pre-cradle position to get ready for Flight Day 2 activities. On Flight Day 2, the crew hits the ground running, and this is going to be a recurring theme throughout the mission. They're going to hit the ground running. Of course, along with the planned rendezvous burns and EME checkouts, the crew will be doing docking ring extension to get the vehicle ready for rendezvous and docking, and perform TPS surveys, Tile Protective System surveys, which will take up the majority of the day. The first surveys will be of the reinforced carbon-carbon, or RCC, using the laser dynamic range imager, LDRI, same thing we did for 114. Again, we tweaked them up a bit based on lessons learned from the mission. So if we can go ahead and roll the video there. You see we're unberthing the OBSS, and here we're starting the starboard wing leading edge survey. And these, of course, have been sped up. The whole inspection process, from unberth to rebirth, and all the wing leading edges and the nose cap takes about 6.5 hours of the crew time. It's a very intense arm operations, and there's 3 crew supporting this for the entire 6.5 hours. What you can see here is what we do is on each wing leading edge we do 6 passes to cover the entire wing leading edge, top and bottom. And of course, while we're doing this, we optimize our attitudes, both to make sure we meet all the LDRI constraints, no sun inside it, but also to maximize KU so we can reduce the playback requirements. What's happening is for the LDRI, that gets recorded on digital tape, and we have to either get it down in real time or play it back later on so the folks can analyze it on the ground. Okay, we're still on the starboard side. Can speed it up enough for you guys. Here's a nose cap. And again, 3 crew are monitoring this the whole time just because of the clearances of the vehicle and to the payload bay and such. Let's see what else I can say here. There's the port side. I'm sure you guys know this, but the actual data we take in the scans is about 20 minutes each wing leading edge and about 20 minutes on the nose caps, actual data. Most of the time spent in each procedure is requirements to move the arm. I'm sorry, 20 minutes of data? Yes, sir, for each wing. Actual data that we get balanced. And I had more to talk about, but obviously I said it too fast. But again, you know, like I said, this is a long crew day getting all this very arm-intensive work done. Of course, after we do the LDRI surveys, we go ahead and berth the OBSS, and we end up doing our one last survey on that day. We call it the crew cabin survey, and we use the RMS end effector camera, if we can get the video going here. Of course, this is sped up again, and this takes about an hour to get done, and basically we're just inspecting the entire crew cabin. We don't require the LDRI for these inspections, because we can get the proper resolution just using the end effector camera. We do this, we do have a constraint of daylight of getting this done. So what the crew does is before daylight, they'll get the arm all positioned and ready to start the survey. Same thing that was done on STS-121. Again, this is still an arm-intensive day, but at least we got rid of the 50-foot boom, and just have to press on just using the RMS. Next time I'll know to speed it up a little bit more. We'll run out of things to say. What they're doing is it's both manual inputs and auto sequences that they put in for this. So they'll go up and they'll get to a certain point, and then they'll put an auto sequence in, and then it'll run the auto sequence to do some of the scanning. And what they do is usually do the manual stuff when they're really close, when they're have closer clearances, and once they get to a specific spot, they'll go ahead and put the auto sequence in, knowing that they're not going to get any closer during the vehicle than what they have. And of course, these are procedures, like I said, that were developed on 114, and we even doubly verified them for 121 to make sure they're being executed safely. The last major task on Flight Bay 2 before we go to bed is the rendezvous tools checkout. So the crew will set up all the TDSCs, their laptops, get them all set up and ready to go for rendezvous the next day. Flight Bay 3, again, hit the ground running as they prepare to execute rendezvous and docking activity. What we're going to do, of course, on 121 is the same rendezvous pitch maneuver that we did during 114 to get some additional inspection of the orbiter belly. And in addition, what we've added on 121 is, last night I'm sure you heard about the gap fillers, but we're going to take some additional photography to try to determine if we see any gap filler protrusions on the bottom of the vehicle. And additionally, we're going to add some additional 800 millimeter shots. There was some criteria as we got after 114 of damage criteria on the bottom of the vehicle, and we want to take some additional 800 millimeter shots because that just gives a better resolution to determine that. Let's see, again, we don't expect to identify anything. It just provides additional assurance that the vehicle is in good configuration. Let's go ahead and roll it there. There we go. See the crew taking the photography. Here's the additional shots that we put in for the gap fillers. That's the 400 millimeter ones. And of course, RPM, expect the same neat pictures that we saw during 114 for this. Some more photos. One of the things that we did update again from 114 is since the 800 millimeter photos are higher resolution, we make sure the crew gets those to the ground first, so the imagery folks can take a look at that. Those first, and then the 400 will give you the broader views. These are the other ones for front to back, and this is back to front for the gap fillers. And before the crew was taking pictures at this time, it was more for PAO, nice neat pictures, but now we're making them work and taking them for the gap fillers. See where they press on. Let's see the lights here. Pressing on with docking here. And then from the R-bar, when we do the Torva emit to the V-bar, it's twice orbital rate V-bar approach. It takes about 11 minutes, and you see the crew here, they're on the V-bar approaching us. They may stop at 30 feet here to see it, and they call this a fly out, and just to make sure that the relative attitude's cleaned up so we can press on in, since we have to get a tight corridor from 30 feet in. And you see we're pressed and we're docked. Of course, after the crew sets up for hatch opening and welcome ceremonies, we put them back to work. Tomas Ryder is transferred over to the station and officially becomes a ISS crew member, and Rick will talk a little bit more about what the official means, what equipment and such they need to make it official. We start doing the mid-deck transfers. And of course, the EVA crew will start doing their EMU transfers over the station side, getting ready for EVAs a couple days later. Of course, since the next major ARM activity is doing the ODSS, over the boom sensor system handoff activities, and same thing we did on 114. Of course, we can't directly reach the ODSS with the shuttle arm, so we have to do handoff operations using the SSRMS. So if we want to roll the video, we can look at that real quick. This is because we have two arms in motion. This is a tightly choreographed operation. What we do is Stephanie and Lisa will be over on the station side doing the station RMS, and Steve Lindsay and Mike Fossum will be doing the orbiter RMS. You can see again, sped up. This takes about 3 hours to get completed. It's because we have to move slow and make sure we don't hit anything. And picture is a little bit deceiving, but we are far away from the SSRMS. And right now, the final position of the boom and arm is in the MPLM viewing position. See, flight day 4, again, the broken record, but the crew hits the ground running. The major activity today is the MPLM install, which Rick will cover later on. And another activity we have, we've been taking we have all the imagery data during ascent. We do the flight day 2 inspection. We do the flight day 2 photography. Flight day 2 inspection, flight day 3 photography. And if the imagery folks identify any areas of concern, on flight day 4 we do a focused inspection of any particular area that they're concerned about. And to accommodate that, we have to go ahead and walk the SSRMS off to the mobile servicer-based system. Let's see if we'll go ahead and roll that. And right now the MBS is located on worksite 4. So you can see we walked it off from the lab, and we maneuver it to a position where it will give us good monitoring cues for the focus inspection. And after we perform the focus inspection, what we end up doing, and we'll talk about that later, is walk back over to the lab prior to sleep that night, and we stay double grappled overnight. And Rick will talk a little bit more about this, but the reason why we're doing this is that right now, you probably heard that the mobile servicing system is single strain because of the inadvertent cut of the nadir cable. See what the crew's doing. They'll go ahead and do the EVA 1 prep activities on flight day 4, get ready for flight day 5 EVA. Okay, flight day 5. Flight day 5 is the first of 2 scheduled EVAs, and we'll be executing them out of the ISS airlock. If you remember on 114, we executed the EVAs out of the shuttle airlock. Well, they replaced heat exchanger that we had concerns before 114, and the airlock is good to go. As a matter of fact, they used it for a staged EVA. And again, Tomas will be later on today. We'll giving you a detailed briefing of the EVA, but just wanted to give you a quick overview of what we'll be doing. It's a 2-parter EVA, and the first part is we want to get the mobile transporter configured to allow us to translate it. Right now, I know Tomas will talk about it. It's in a configuration where the cable is outside and we can't translate it. Second part of the EVA will be doing the DTO 849. Basically what we're going to, like I talked about, evaluate using the orbiter boom sensor system as a TPS repair worksite. Flight day 6, I'll put slower pace in here, but the entire day is basically for transfer ops, and of course the crew is doing EVA 2 prep activities. Flight day 7, we'll be doing EVA number 2, which is TUS R&R activities. Rick will be giving you more of an overview, and again, Tomas will be discussing specifics later on. Flight day 8, more transfer, and the plan here is after we get the TUS and R&R completed, we're going to move the mobile transporter from worksite 5 to worksite 4 to get ready for activities on flight day 10. Okay, flight day 9. The crew will be doing the final MPLM transfers and rack configuration, and they'll have 6 hours of well-deserved off-duty time. And Rick will go ahead and provide you more details of the wreck-up of the transfer tally, what we transferred over and what are we returning. Flight day 10, the activities include the final MPLM closeout. Then we'll return the MPLM back to the payload bay. Again, Rick will give an overview of that. The EVA crew will transfer their EMEs back to the shuttle. We'll be doing a walk-off the SSRMS to worksite 4 as we shown previously. And that's in prep, like I said, for the first part of late inspection activities that we've been asked to do by the program. Let's see, and as part of the late inspection activity, we can go ahead and do one of the inspections docked, and what we'll be doing is the port wing survey, exactly what we used on Flight Day 2 because we have the proper clearances. And let's see if we can roll the video and just kind of show you, this is a docked port wing survey. Of course, we still are concerned about clearances and such, but as we reviewed this, we meet the standard 5-foot clearances and more of the elbow and lab clearance issues, just to show you how sporting this is going to be when we do it docked. And again, this is the first of the 3 inspections we'll be doing for the late inspection requirement. That's for concerns of MMOD damage while we're on orbit. So after we complete the port wing inspection, one of the things that we're going to do differently than we did on 114 is we're going to undock with the OBSS in the handoff position, and I'll get the split of that. You can see it's in the handoff position here. Usually we would have had berthed it, put the arm away, but to allow us to get the additional 2 inspections and not violate any crew timeline constraints, we're undocking with the OBSS in this position right here. And for 114, it was a contingency only type of scenario, and we've gotten that position certified for 121 use. See, Flight Day 11 is undocking day, and due to the late inspection requirements, we will not be doing the fly around, the entire 360 fly around. We'll be getting a freebie quarter fly around on this part of that. See, also, in support of our late inspection, we have a re-rendezvous plan that we set up, and basically we have changed some of the set burns to allow us to, or provide us the capability to re-rendezvous to the station if required, and based on what any of the assessment of the late inspection provides us. So if we want to go ahead and roll the video real quick here. Stand it back off to 400 feet. And our first set burns about 1.5 feet a second. We kind of do another 12 maneuver to stay in that position, and then our sub 2 is about 28 minutes later. So that happened really quick, and it's a 1 foot a second posigrade. And what that's going to do for us, it's going to keep the orbiter above and behind the ISS to provide that re-rendezvous capability. See, after undock, we will complete both the starboard wing and nose cap surveys essentially the same way we did them on Flight Day 2. And after the crew completes those surveys, we'll go ahead and berth the OBSS, and then we'll berth the RMS. Flight Day 12 consists of the standard end of mission -1 entry prep activities, the FCS checkout, RCS hot fire, cabin stow, KU stow, and of course tearing down the PGSC network. So on Flight Day 13, right now it's deorbit planned landing at KSC. We talked. We'll give you the overview, or as we mentioned previously, if the cryo is available, we plan on extending the day, or plan on extending the dock duration by 1 day. What that allows us to do is go ahead and schedule EVA number 3, and what I said before was consists about the IR camera checkout and the NOAX RCC repairs. And the extra day, we'll insert that after Flight Day 9. So Flight Day 9 will be the EVA number 3, and then we'll move the Flight Day 9 activities to Flight Day 10 and so forth and so forth. So MPLM berth will be Flight Day 11, on dock Flight Day 12, entry prep Flight Day 13, and deorbit Flight Day 13. Let's see, and that's all I had, and then I'll hand it over to Rick to talk to the station part of it.
Thanks, Tony, and thanks to everyone, all of y'all, for showing up today. All of us here at NASA, we realize the importance of public opinion has of us, and as such, we rely heavily on you all to bring that story to them. So thank you for your interest in this mission and coming out and supporting us. Let's see. Before I get started, I'm going to apologize right off the top here. We talk in acronyms. That's a way of life here, and I know I'm going to use them. I'm going to try and spell them out the best I can. But if I forget, by all means, please at the end, please either catch me or in your question and answer session, go ahead and ask it, and Kylie will make sure that won't count against their allocation, right? So, okay, what I'm going to cover today is I'll start with a quick status of the Expedition 13 crew and the status of the vehicle, the station. And then I'll talk, like Tony said, about some of the more significant station-related activities that we're going to accomplish throughout our mission. And then I'll conclude with some information on the flight directors that will be supporting the shuttle operations during the mission. So, with that, as far as the on-orbit status, the Expedition 13 crew, Jeff Williams and Pavel Vinogradov, they're doing very well. I know in the previous presentation, Kirk Shireman gave you some details on what they've accomplished thus far. They're doing well, as I said, and we're not tracking any vehicle problems. Some of the things I'll be doing through the course of the remainder of this month is a lot of it's going to be dedicated towards getting ready for our arrival. And some of the significant things I'll be doing is they'll concentrate a lot on the pre-packing of the cargo that's going to be transferred over to the multi-purpose logistic module when we get there. In addition to that, we do regular conferences with the team on the ground that's putting together a transfer plan. That's just to make sure everything's going as planned and answer any questions that the crew may have. Similar to any mission that we're going to be using the robotics arms, we do an on-orbit checkout prior to the flight of the Canadarm2, the SSRMS. So we're going to be doing that, and it's really, it entails bringing it up on both strings, doing some grapples, some releases, just to basically make sure everything's functioning as we need it to before we get there. Tony talked about the R-bar pitch maneuver that the shuttle does before during the rendezvous sequence. We have training sessions for the crew. It's not that difficult of a task, but it's a little bit different. You know, they're taking pictures out of the service module windows. They get themselves comfortable with how they set up their cameras and the comms set up for it. So we do some training sessions, and then we also have some conferences if they have questions as well. And then, just like we do on any other mission, is we do a timeline review for the crew. They walk through the whole timeline, check out what we're going to be doing throughout the mission. They assess the procedures, review the procedures, and then we have associated conferences with the ground flight control team and the 121 crew. We'll have conferences, and that way we can work out any questions that the crew may have before the shuttle shows up. So let's see, major activities that we're going to try and accomplish during the flight. You've heard multiple times that we're going to get back to a three-person crew. Some of the details on Thomas Ryder's transfer, as Tony said, right after docking and the welcome ceremonies, we get to work, and what the primary objectives for getting a crew member over on the station, the designated as a station crew member, is we have to transfer his IELK, and I apologize, that's a Russian acronym, and I don't know what it means, but it's a seat liner that goes in the Soyuz vehicle, and it's specific to each crew member. So we got to get that transferred over into the Soyuz and installed, and then we also do a pressure check of his pressure suit, make sure it's going to circle suit, make sure it's going to hold pressure. Once that is completed, he is now designated as flight engineer number 2, and we're the three-person crew. And for the folks who like to keep track of his statistics, we're anticipating that to occur at mission elapsed time 2 days, 0 hours, and 45 minutes. Mr. Ryder is scheduled to stay on orbit for 175 days, and he'll be returning on STS-121, the 12A.1 mission. That's our first order of business, and we have a check box on the transfer checklist to make sure it's checked and say that Thomas is on the other side of the hatch when they undock. It's a joke. All right, leads me into the multi-purpose logistic module, MPLM. This one's named Leonardo. We're going to be installing on Flight Day 4, and I have a video clip, if you'd roll that, please. This is very similar to the way we did it on 114. I should say it's exact. We're using Canadarm2 to grab it out of the payload bay, and this will be performed by Stephanie Wilson and Lisa Nowak. And we're just going to lift it up, and we're going to put it right on the nadir port, which is the bottom port of the Unity module, or our node. And the whole process in itself takes on the order of 4 hours. But the last hour of that is really just the bolting up of the mechanisms. Okay. Now I'll go through a list of some of the contents, some significant items that we have internal to the module that we'll be transferring. Kirk's covered some of this, so I apologize for the repeat, but I'll be covering some of the other items as well. Let's go ahead and run the clip of the module, please. It is full, that's for sure. You'll see there's some empty bays, and what those empty bays allow the crew to do is to get access to all the cargo that's internal to it. All right. First type of rack we have is a resupply stowage platform. We're going to have 5 of these guys on orbit. Each one of you can see they stow luggage on both the front and the back of these racks. That's why we have empty bays that allows them easier access to the back side of the racks. And we also have 3 resupply stowage racks. You see these are a series of drawers, and you basically can take the drawers out and the contents and just transfer those over. As I said, we have 3 of those. Kirk mentioned about the oxygen generator system. It's a very similar apparatus as we have on orbit in the Russian side with the Electron. We're not going to be using it during stage. It's not going to be used until the 13A stage. The other rack we have is Express Transfer Rack, and you can see this is a payload that's EMCS, which is the European Modular Cultivation System. It's basically a gravitational biology type payload. Thomas will be starting to use that during our stage after the shuttle leaves. Here's a continued look of how this thing's laid out. On one of the other resupply stowage platforms, we also have a heat exchanger that we'll be replacing in the laboratory. It's been having some problems, so we're going to go ahead and just pull it off and replace the one that's on orbit. It won't be installed completely until after we leave. We have 2 of them. That heat exchanger goes to what we call the common cabin air assembly, which is a fancy name for air conditioner. Melfi is the minus 80-degree laboratory freezer for ISS. It's a freezer, and it's going to be used for the popsicles. I mean, it's going to be used for science samples to preserve them. So this is a good depiction on how everything's laid out. Let's see. As far as the amount of cargo, a lot of people like to keep track of these numbers. For the asset manifest, we have about 5,100 pounds of cargo, and it equates to, if you're familiar with a CTB is a crew transfer bag. I can't really give you dimensions, but they're so big. We have about 177 of those that'll be equivalent. Now, some of them may come in different sizes, singles, doubles, and the big triples. But there'd be 177 of those guys transferred over. All right, then on Flight Day 10, we'll be putting the payload, uninstalling and putting the payload bay back into the shuttle. We'll be taking the MPLM off the station and putting it back in the shuttle payload bay, and I have a clip of that as well. It's again, it's exactly what we did on 114. You'll notice that it's kind of interesting that we do a kind of a peculiar flip around. which wasn't observed when we did that, when we did the install. And we did this because we had to come up with a different arm configuration to provide clearance. Where that MPLM is installed on the native port, you have some clearance issues if we have a Russian vehicle docked on the FUB native port and solar is deployed. So we came up with a different arm configuration. So when we pull this off, we got to do a flip around and then we can put it in the payload bay. This whole activity is going to take about 3.5 hours, and the first 45 minutes is just unbolting it from the station. As far as the return manifest, I'll let this finish here. There we go. As far as where we're going to be returning cargo-wise, we're looking at around 4,700 pounds of cargo and 133 of those cargo transfer bags or crew transfer bags. All right. Next item of interest is the first that we're going to be doing on our mission. During increment or expedition 12, Bill MacArthur installed a piece of hardware called the RUBA. And the reason we call it RUBA is because its acronym is Recharge Oxygen Orifice Bypass Assembly. That's why we use acronyms. Anyway, it's a line that actually is bypassing a restrictor, a flow restrictor in the O2 transfer line that is used to transfer oxygen from the shuttle into the station, into our tanks on the external part of the airlock. In the past, we've had an issue with the crew when they go to perform their exercise protocol portion of an EVA prep. They weren't getting sufficient flow, mass flow when they're doing when they're riding on the cycloergometers. So we designed the RUBA, which just basically bypasses that flow restrictor. All right. So we had it installed on Expedition 12. So our plan is to right after docking, the crew's going to set up for O2 transfer, and we're going to pressurize that line because it's never been pressurized before. And then we'll isolate it, and during the crew sleep on flight day 3, we'll basically do a pressure check. The next morning when we get up, we'll look at the pressures in the line, and if it's sound, then what we plan on doing on flight day 4 is actually have the crew go and do their exercise portion of the protocol. It's they basically, each one of them will get on the cycloergometer and with the mask on, and they exercise for 10 minutes. So this will verify that we get enough flow through the masks using this RUBA. So if we have an issue, like we're not getting enough flow or we don't pass the leak check, then we'll use the standard procedures that we've used in the past, and that is we run hoses all the way from the shuttle launch and entry helmet ports to supply the required O2 during the exercise part of it. Okay, that's all for RUBA. Let's see, you've heard a lot about some of the activities that are going to occur during EVA-2. Both Kirk Shireman and Tony talked a little bit about it. We saw some of the information and some of the pictures. But I'll give a little bit of an overview on what we're going to accomplish on that. Let's see, the first ORU that we're going to transfer is the pump module, and I have a picture of it a clip of it, or a picture of it in the ICC. It's the same as you've seen like 3 times already today. Anyway, this is where it starts. It'll end up getting transferred up to the external platform during the EVA, and Tim also give you all the details, but we'll use the arm to transfer it up there. What this pump module is actually it's going to be a spare pump for our pumps that pump ammonia through the radiators on our external radiator system. So the next clip I think will show where it's being located on ESP2. Okay. The other primary objective of this EVA is to replace the failed trailing umbilical system wheel assembly. Again, you've heard a lot about that. I think Kurt mentioned that it provides a redundant command and telemetry path to the mobile transporter, and also the Canada ARM-2 when it's stationed on the MT. Folks probably remember that back in December of last year we had an inadvertent cut of the cable, and that's why we're having to replace it. I think I have a picture of it on the ICC as well, just like you saw on Tony's and Kurt's pitch. Okay, again, and this guy's going to be transferred up to the S0 where they're located by the arm, but they're going to be there's going to be a crew member on the end of the arm, and he'll be holding it as we take it up there. This is the location where we're going to install this. This is the nadir one. There's the one up kind of on the top side of the truss. It's the zenith one. But this is the one that we're going to replace during our mission here. The failed one, or the old one, the one that has the cut cable, is actually going to be put right back onto the ICC where the new one came up on. And I think we have like a wide view of the whole. There's the mobile transporter. Talked about. Tony mentioned how we were going to have to move the mobile transporter down to worksite 5, and that's to get it out of the way, which I can't see in my picture because of the glare, but the two seated carts are in between the mobile transporter and where we're going to be doing the activity. So we have to, where the MT is located right now would be right over top of that assembly, where the test is. So we had to move it out of the way in order to allow the EVA guys to get access to it, or easier access to it. If we end up not moving the mobile transporter, then there's a lot of extra overhead that Tim Moss is going to tell you all about. The other part of this R&R is where the cable comes from the TUS and then attaches to the mobile transporter. It's called a interface umbilical assembly. The TUS it's a ribbon cable, similar like what you'd see in your computer. Just has lines of power, data, and video. And where it attaches to the mobile transporter, there's a block, if you will, that fits into a cutting assembly. And then from the other side of the block, the actual normal cables come out and provide connections to the MT. Since that mechanism fired, we can't put the cable into it, so we got to replace that umbilical interface umbilical assembly as well with a new one. The new one's going to have that cutting mechanism disabled, so we don't get another inadvertent cut of a cable. Okay, well, let's see. That's really the highlight of the major ISS-related activities we're going to be doing during the flight. What I'd like to cover now are the flight directors that we support in the mission. Our first one is Annette Hasbrook. She supported the previous STS-121 9A docked mission, and she was also the lead for Expedition 10. She'll be supporting the Orbit 1 shift. I'll be supporting the Orbit 2 shift. I was previous lead on STS-102, or the 5A.1 mission, also 111, which was a UF2 mission. And then also I was one of the expedition leads for increments 2 and 5. And lastly, on the Orbit 3 shift will be Matt Abbott. This is going to be his first dock mission, so he's excited. And he was also, you may recognize him, he was the lead for Expedition 9 as well. Those were 6-month stints, very intense. So that's our flight director team. Thank you all very much.
All right, now we'll start with questions from here and other NASA centers. So we'll start over here on this side of the room. Please state your name and affiliation. If you can, direct it to one of the panelists.
Mark Carreau from the Houston Chronicle. For Rick, what are you eager to get off the station in terms of equipment cargo that's taking up space that you need for operations?
Okay, there's a lot. As folks are well aware, our storage situation is challenging because we have so much, and we haven't been flying shuttles in a continuous effort, so we've accumulated quite a lot of items. I think our first priority of things are items that maybe have failed, but we want to do get a feel for what caused the problem. That interface the heat exchanger on the cabin common cabin air assembly, the CCAA. That would be one of the items. There's a lot of sample type things, both water, air samples that we take to continuously monitor the environment. Those kind of things will be returned. There's quite a few Coors antennas that are used for the Russian vehicle dockings, and the Russian team, they refurbish those, and so we'll get those back so they can refurbish those. So I think that kind of categorizes. There's a lot of stuff, but those are probably the more significant items. I'm sure there's others that I could probably give you more information on.
Alan Boyle with MSNBC. For Tony, I wanted to ask how the timeline might change, how quickly it might change if something did pop up during the inspections that needed repair. And for Rick, I wondered what the role of the ISS crew might be in that eventuality.
Okay, I'll tackle the first part. Basically, you know, we do all those 3 days of intensive inspection and imagery, and Flight Day 4, you know, we look at if there's any area of interest to determine if anything additional needs to be done. So we do the focus inspection on whatever their damaged area is, and we'll take a look at that and see if there's any additional work that needs to be done, whether we need to do an EVA or not. What our plan is for the flight is EVA 1 is pretty critical in the fact that we need its prep activities for the TUS, which is important to do. And of course, one of the big key things we want to understand is how good the OBSS is for a repair platform. So we'll be doing that EVA for sure. EVA 2, of course, the TUS R&R. And so if we have to do any additional EVAs for repair and such, probably EVA 3 is where that would occur. And of course, that gives us time. We'll get our first 2 EVAs that are mandatory to get done, and then gives us time after Flight Day 4 to understand where the damage area is, and then give the EVA folks and the ARM folks time to plan out a repair if required.
And as far as the station crew's support of those efforts, it would probably be minimal, mainly because it was the shuttle crew, both the EV crew members and also the ARM operators that have done most of this training and are more familiar with these type of techniques. Obviously, Jeff Williams has used the Canadarm2 on orbit, and so he could probably provide some assistance in whatever ARM ops they're going to be doing. Plus, going out of the station airlock, we always have a station crew member that helps with some of those operations. But other than that, I think that'd probably be what they would be limited to.
Irene Klotz with Reuters. 2 questions for Rick. The first is Thomas Reiter and the program prepared to have him stay aboard the station if there's delays in the 116 mission, and if there's any contingencies to have him fly home on Soyuz, if there's any seats available? And then the second question, regarding the spares that are going on station with this shuttle flight, as the program's flights to the station are numbered now, is there any plan in place to look at being able to launch some of these things like the palm seat exchangers on other vehicles besides the shuttle?
Okay, first question. It would have been probably more appropriate to ask Kirk Shireman on the previous briefing, but I can talk to the fact that, you know, we include skip cycles in all of our planning for consumables. So in that regard, having Mr. Reiter stay longer is not an issue. And then there's a series of options for his transfer. You know, we do have a Soyuz mission coming up that has a 3rd seat that I believe is a paying customer that obviously could be displaced if the programs decided that was the right thing to do to bring Thomas home. So 1, we can stay longer. He could stay longer if need be, and then 2, there's other options that if we need to bring him back. Okay. Let's see the second question. Spares, yes. And you ask a good question, and the answer is yes. The program has a group of folks that are solely dedicated on looking at what are the implications of ending shuttle flights in 2010, and it is a big effort on trying to make sure we're getting all the spares that we deem required on orbit before that time period. So yes, people are working very hard, and we're trying to work the manifest, and it is a challenge, you know, to continue with assembly, but also plan for these kind of things. Well, and as far as other vehicles, you know, we have other vehicles coming online with the automated transfer vehicle, ATV. That's going to be able to support a lot of cargo, and as well as the HTV. So those are still, you know, in the works, and I'm sure the team that's putting together this whole sparing plan is considering these other vehicles.
Bill Harwood, CBS, over here for Tony. You mentioned on-pad hold time. If you launch on the first day, do you already have the predicted consumables for the mission extension, and how does that drop off as you move into that on-pad hold time?
Yeah, we can delay up to 2 days and get the 13-day mission. So the first attempt, you know, just based straight on cryo, we can get it. And of course, we'll hold off saying that we have the extra day until we get on orbit and make sure we stabilize as far as power usage and such, and wait till we get docked and make sure we're all happy with what our predictions are. But based solely on our predictions right now, we can delay 2 days and get the 13th day built.
Todd Halverson of Florida Today for Tony. On DTO 849, what are the chances of an inadvertent separation of the OBSS and the RMS with a guy on the end of the arm, and what contingency plans are in place should that crop up, and are there any operational workarounds that you have put in place for that eventuality?
So answer your first question, very low probability. I mean, we're grappled using the RMS. We haven't had any failures to date of the end effector and the grapple fixture and such, holding on. And so we feel very confident because, you know, we depend on that pod for the, you know, doing the standard payload, moving payloads here and there. So we feel very comfortable with that. Second question, we have contingency procedures, even the EVA checklist, if we had an inadvertent release. And I know Tomas will talk about this in more detail, but we have the crews on 85-foot tethers that are attached to the SRMS. So if the boom did come loose, they're attached to the orbiter still, and then the boom could go wherever it goes after it releases.
Jim over at NBC. Back to the issue of the extra day, Tony. Thanks for clarifying on how you earn it, how you earn the extra day. If you launch on day one, how would you possibly earn a second extra day? Are you looking at that, and where would you insert the extra day normally if you have a plan?
Yeah, it's going to be I don't want to say a struggle, but if we launch the first or second day, we know, you know, like I said, via our predictions, we know we'll get a pretty good chance of getting that 13th day. But after that, you'd have to require a pretty significant orbiter power down, Jim, to look at getting another day. And I can't give you the specifics right now, but I mean, the crew's going to do their best, even if we launch on the second day, you know, turn down lighting and, you know, do the standard things they do to try to conserve cryos. But to get another day on top of the 13th would be a challenge. We're going to look at probably waiting to flight day 5 to make it official if we have the extra day or not. Like I said, that's just to make sure we're all happy with what our predictions were, both undocked and docked, and make sure we have our electrical predictions correct and cryo usage correct.
Hi, I'm Nancy Holland from KHOE-TV. I want to go back to those late inspections a little bit and just get you to sort of concisely summarize exactly, if you can give me a comparison of what this would be like trying to do here on Earth, the constraints that you might have, the area you have to operate in, what the challenges are, and also exactly what it is you're looking for. And thanks in advance for not using those acronyms.
Well, I would look at it, to simplify it, I guess doing crane operations, and all you have is really TVs to look at, all the clearances and all the monitors. You don't have the actual visibility, like a bird's eye view to check out everything. We have applications that, you know, provide those views and such, but it's more of, okay, checklist says this, let's check this view, let's check that. So it's basically like a video game, trying to do a video game and watching the video monitor in front of you and while things are moving around you. I guess I know that's simplistic, but does that answer what you're looking for?
And what exactly are you looking for?
For the Flight Day 2 inspections, They're looking for any ascent debris impacts. So any birds or ice or foam that may come off, they want to make sure that the vehicle's clean based on going through the ascent environment. For the late inspections, it's more about NMOD concern, micrometeorite damage.
Kate Tobin with CNN. My question is also related to the late inspections. What prompted the addition of these activities? Was it ever considered for STS-114? What happened between now and then that prompted you to add this? And if you find something, it's awfully late in the game to do anything about it. What's the plan if you were to find something in a late inspection?
Okay. Yes, it was looked at for 114, and the concern was brought up at the flight readiness review. They took a look at it, but we got to the point where we were too close to the mission to incorporate doing the late inspection. And of course, the managers looked at the risks and what they were taking, and they all agreed that we were too close to flight, and it was more of a risk to try to incorporate it into 114 than to not. For 121, we talked about it, and we've been working this probably for 8 months or so, taking a look at how we can fit it in without impacting the mission objectives that we've been working to for 2 years, and we've come up with a pretty good plan. The folks that brought it up, of course, the standard, the safety folks came in. NMOD damage is second on the list for the orbiter PRA analysis. Ascent debris is, I think, 28%. NMOD comes in at about 22%. So there was concerns about it, and there was originally a programmatic document that said as long as we're above 1 in 200, that was a risk that we were willing to accept. And with the capability to do all the inspections and such, the folks started looking at, well, is there anything we can do to increase those probabilities or decrease it? So that's, and if we find something, right now, like I told you previously, we have a plan of rendezvous. It's not a programmatic requirement, but we're protecting that in case we find something, people don't understand, we can get back to the station. We'll have limited days that we'll be able to do anything with, but we can at least get to a safe haven, so to speak, so we can talk about it.
Tracy Watson, USA Today for Mr. Stakachi. You've described a lot of, I guess really for both of you, you've described a lot of robotic operations on this flight. How would you characterize the amount of robotic ops you're doing compared to previous flights and the complexity of those?
Well, I mean, for starters, it's almost identical to what they did on 114 with the addition of the late inspection, Anthony? I mean, you characterize it the same?
It's kind of like what we're doing for all the late inspections. It's more of the clearance and being very close to the vehicle as you're going through this whole starboard nose cap and port. Using the arm before, like for the Hubble, you grab the Hubble and throw it in the bay, or for any other pin, like even the MTLM, you pick it up and you go ahead and install it on the node. And a lot of the other arm operations, usually they're picking up a payload or that's over the payload bay, and you have very good visual cues and monitoring. With the late inspection, like I'd answered previously, you're doing a lot of it blind, where you're dependent on your cameras outside the orbiter and your digital data and such to make sure you meet the clearances. Of course, we're very comfortable in doing that because we PV'd all this and we understand the clearances and what we're looking for. But it's just more intense because the crew has to watch it, watch it continuously for that, 6.5 hours.
Okay, and I understand we have a question from NASA headquarters, so we'll take that next.
Yes, this is Seth Borenstein from Associated Press for Tony. Can you go through the scenarios if you that you would have for not getting that extra day? In other words, what type of delay launch scenarios would give you no 13th day? And if that's the case, and you require TPS repair on orbit, you don't have that extra. I guess you don't have that third EVA day. What don't you do so you can do the TPS on orbit? In other words, what do you dump so you can do the TPS repair?
Okay, so what would impact us, the big thing is if we delay launch after the second opportunity. The more we delay, we have crowd that boils off on the pad, so we don't have the crowd to make the electricity. The plan is to kind of look at it smartly. You know, we're launching in July, and the thunderstorms in the afternoon make it challenging getting the vehicle launched. So what to look at is what crowd we have available if we do delay, and if they should stand down and replenish the cryos or not to try to get some more opportunities. But the key thing is if we go past not looking at any of that, but if we go past the second day, we've lost second opportunity, or third opportunity, basically, 48-hour delay. We don't have the 13 days. As far as the scenario where if we didn't get the 13th day and we did see some TPS damage, you know, you're looking at possibly giving up one of your contingency days at the end of the mission. Then we have both a weather contingency day and a systems contingency day. You might have to give up one of those if you need to do an EVA to do the repair. So there's some days you can give up, but you also are giving up other contingency activities.
So that's all the time we have for this briefing. And now we have our spacewalk overview, which is also known as EVA, or extravehicular activity. And to brief this activity, we have the lead EVA officer, Tomas Gonzalez-Torres, to talk about the EVAs for STS-121. We'll open up with opening remarks as usual, and then have questions from the NASA centers. Tomas?
Thank you, Kylie, and thank you all for coming to the EVA 121, STS-121 EVA briefing. I'd like to start off by thanking the excellent team that I've had an opportunity to work with in preparation for this mission. In the back room, the EVA back room, as the task lead is Karina Shook, as the EMU lead is Ed Tom, the task OJT is Gail Schneider, the EMU OJT is Dave Oswald, and the EVA airlock console position is Roger Loutridge. The people that I just mentioned and myself are a very small part of an excellent team throughout NASA and Johnson Space Center in preparation for this mission, and I just want to thank everyone else that has also helped with that. In addition, I want to thank those people with whom, of course, we would not be here today, the crew of STS-121. They have been an excellent crew to work with, very talented, hardworking people, and just all-around great people. EV1 for this mission is Pierce Sellers. His previous flight was on 9A, where he was the EV2 on that flight, and he performed 3 EVAs. On this mission, he will be the EV1 for the flight. You will be able to distinguish him from the other crew member because he will be wearing the solid red stripe. The EV2 for this flight will be Mike Fossum. This will be his first flight into space, so obviously his first EVAs as well. For every mission, there is a crew member that will coordinate the choreography and the procedures that the crew will be performing. This will be Mark Kelly. He's also the pilot, so he's been pulling double duty in preparations for this flight. For this flight, we will be flying 3 EMUs, 2 larges and 1 extra large. The 2 larges will be the primary suits for Pierce Sellers and Mike Fossum. The third one, the extra large, will be pre-positioned for future station assembly EVAs. These 3 suits will have a new enhanced caution warning system. This will be the first time these suits are flown up with this new enhanced caution warning system, and the first EVAs with this system. The differences between the old and the new are mostly hardware upgrades. The caution warning system provides status and monitoring of the suit and provides information to the crew and to the ground to tell us whether or not there's a problem with the suits so that we can act accordingly. As I mentioned, the major differences between the old and the new caution warning systems were basically hardware upgrades. Because of the hardware upgrades, we also had to do software upgrades. Other than that, the majority of the differences are fairly transparent to the crew. EMU checkout will happen on flight day 2, and then on flight day 4, the crew will prepare for the first EVA, which will occur on flight day 5. The checkout of the third extra-large suit that is not planned on being used will happen on flight day 6, along with preparations for the second EVA. The third EVA right now is unscheduled, and if it does occur, it will happen on flight day 9. The suits will be fully swapped out. The 3 new suits that we're flying up will be left on station, and the 3 that are currently up there will be brought back home. And what I'd like to do at this point is go through a quick summary of what's going to happen on the first EVA, and then we'll go through in detail with the video. The first task of the first EVA will be the installation of an item that's called the blade blocker, and that's this item right here. This will be installed into the Zenith IUA, which is the interface umbilical assembly. And if I could get the still shot of the IUA, please. There are two IUAs which are located on the MT and the MBS. The IUA is the interface umbilical assembly, and it is the interface between the TUS, which is the trailing umbilical system, and the MT and the MBS. The TUS is basically an extension cord that provides power and data to the MT, which is the mobile transporter, and the MBS, which is the mobile base system. This system is a mobile platform that can move along the forward structure of the station, providing a worksite platform for the station robotic arm. Back in December, as you recall, the Nader IUA inadvertently fired and inadvertently severed the Nader TUS cable. We have two TUSs on station right now, so it basically just cut the redundant cable. In order to prevent the same thing from happening to the Zenith TUS, during a previous EVA earlier this year, the cable was removed from the necessary routing within the IUA. In order to restore that proper routing, we're going to install the blade blocker, which will physically prevent the blade from possibly even severing the Zenith TUS cable. That was a long explanation, but really that's only about the first 30 minutes of the first EVA. After that, the rest of the activities involve the boom DTO, where both crew members will be getting on the tip of the boom for a worksite stability DTO, where we're hoping to establish whether or not the boom is a viable work platform for TPS inspection and repair. And with that, if we can go ahead and start with the video for EVA 1, please. EVA 1 will start with the crew members, Pierce Sellers and Mike Fossum, egressing from the ISS joint airlock. They will be translating up to the Zenith base of the MT and the MBS. This location is the blue flashing area, and this again is the location of the Zenith IUA. The blade blocker will be installed by the crew, and then the cable will be routed back through the IUA. Once that activity is completed, the crew will be done with that activity. It will translate back down towards the joint airlock. Along the way, they will retrieve an ingress aid from the APFR, or the foot restraint that you see flashing down the bottom of the screen. They will retrieve that ingress aid and continue translating aft on station. They will install it on a second foot restraint, which you see now flashing on the left-hand part of the screen. They will retrieve that foot restraint, the tool stanchion, and then they will translate down to the payload bay, along with an additional bag that will contain some hardware that will use for the DTO itself. Once the crew gets down to the payload bay, they will find the shuttle robotic arm and the boom configured as you see in the picture. Their first task will be the temporary stowage of that foot restraint and the bag onto the ICC that's going across the payload bay, and that's the location of the stowage that you see flashing there. Once that's complete, the crew will translate to the shuttle robotic arm, and they will attach their safety tethers at that point. Once that task is complete, the shuttle robotic arm will relocate the boom to provide access to the crew for boom setup activities at the tip. We have several models and several simulators that give us a good understanding of how the boom will behave. However, since this is the first time that we're doing this, for additional stability, we are going to have or pre-position Mike Fossum, which you see in this picture, just forward of the boom in the payload bay. So he will be there in case any additional stability is necessary, as Pierce Sellers, which would be just aft in the payload bay of the boom tip, installs the hardware necessary for the boom DTO. The first piece of hardware that will be installed is called the pad. It's the PFR attachment device. It's the device that physically allows for installation between the foot restraint and the boom tip itself. and that's that first item that you just saw up here. After that, we'll be installing a load cell. This load cell is actually comprised of 4 individual load cells, and this will allow us to record the inputs created by the crew during the DTO. The load cell is the part across the top, the horizontal part of the picture. The pad that I mentioned earlier is the bottom part. This information will be recorded within the pad, and that will be brought back home for analysis and verification of our models and our simulators. Once that installation is complete, the next thing and final will be the foot restraint onto the load cell. After that, Pierce sellers will ingress the foot restraint, and then we'll maneuver to the first DTO position. Position 1 will be located just above the starboard sill of the payload bay, about 14 feet. The entire approach behind the boom DTO is to take baby steps to get an understanding at what we're calling more rigid positions. The crew will perform various inputs in this position that will mimic those that would be requested of a crew member or necessary by a crew member performing TPS inspection and repair activities. At this position, the deflections expected by the boom are less than those expected in other positions, so we want to gain confidence in how the boom is behaving in this position before we continue to others. This is footage of the crew practicing their activities in the neutral buoyancy laboratory. And this is Pierce Sellers. The activity that he just performed is a layback, and these are just some examples of some of the things that you'll see them doing. Some other things that would be required of the crew are just simply getting out of a foot restraint and then getting back in. And the last footage that will be coming up is basically the reconfiguring of a foot restraint, which may be necessary to reach various parts of the vehicle for inspection capabilities or for repair capabilities. Once the crew is complete at position 1, the boom will be maneuvered over to position 2. This will be a very exciting view, I'm sure, for Pierce Sellers. And the maximum expected deflections at any time during the DTO is about 4 feet. This deflection actually occurs over a fairly long period, and so the motion will be fairly slow. We'll repeat some activities at this position 2 to gain more experience at a weaker position compared to the first one. And then the boom will be maneuvered back down to the payload bay sill. Mike Fossum will ingress the foot restraint this time, and Pierce Sellers will free float onto the tool stanchion. Together they will both be maneuvered to our third DTO position. And at this location, both crew members will be performing DTO load inputs simultaneously. They will sometimes take turns, sometimes do it at the same time, but again, they will be practicing and performing some actions that would be required by crew members during a TPS inspection and repair off of the boom tip. Once complete at the third DTO position, we've gained confidence in how the boom is behaving. We're actually going to bring the crew in close to structure over by the port 1 station truss element. Mike Fossum will be on the foot restraint. In his hand, he will have a load measuring, handheld force measuring device. He will then be imparting forces directly into the station truss structure that will be mimicking various types of repairs for both tile and RCC. As he performs these actions, he will be getting a rough feedback of how much force he's imparting, as well as getting the resulting motion on the boom tip. Some of this information or some of the results of the boom action, as I mentioned earlier, will be recorded in the load cell. Some of it will be done with photogrammetry using overlays, which will give us a rough hack of how much the boom is deflecting. And then the rest of the information we'll be gathering is subjective information by the crew themselves, whether or not they feel that from the inputs that they've provided, whether or not the boom is a feasible work platform or if it's moving too much for them to actually enact a repair. As I mentioned earlier, we've had several simulators and analysis that give us a good understanding of how the boom will be behaving. It was also used in training the crew. This was Mike Fossum. That's the handheld force measuring device that you see in his hand. He is on a 6 degree of freedom trainer that as he imparted these forces, it behaved, pushed him away or brought him back, as was believed that the boom will actually perform. Once we're complete at the P1 push position, the crew will be maneuvered back down to the payload bay sill. And at that point, the crew will begin the cleanup activities. The crew will egress the foot restraint, remove the foot restraint from the load cell and the pad from the boom tip. The arm will then be maneuvered back to provide access for the crew's safety tethers from the shuttle robotic arm. The crew will then take all this hardware back up to the space station, stow it back where they got it from, and then they will ingress the joint airlock, and that will be the end of the first EVA. EVA 2 has two major components. The first one is the transfer of the pump module from the orbiter ICC, or the integrated cargo carrier. As was mentioned earlier by Rick LeBrode, the pump module is basically, just as the name says, a pump that provides the circulation of the cooling system on the space station. This is a spare pump module, and it will be temporarily stowed on the external stowage platform on ESP2 up on the station. The second item is what you've all been hearing about, the TESS R&R. Again, the TESS is the trailing umbilical system that provides power and data to the MT and the MBS. So we'll be doing a full change-out of that, bringing home the old TESS and installing the new one. And with that, can we go ahead and have the video for EVA number 2, please? The EVA 2 will begin similar to EVA 1. The crew will egress from the ISS joint airlock, and then they will translate down to the payload bay, retrieving a foot restraint along the way. The pallet that you see across the payload bay, that's the ICC that we mentioned earlier. The large box in the center of the view is the pump module. Pierce Sellers is over on the right-hand part of the screen, and Mike Fossum will be located on the left-hand. Underneath the ICC is an FGB, or a fixed grapple bar. This fixed grapple bar allows for the station robotic arm to grapple the pump module and transfer it over. Pierce Sellers will remove this FGB from underneath the ICC and relocate it onto the forward face of the pump module, along with the help of Mike Fossum. Once this is complete, again, this allows the capability for the station robotic arm to grapple the pump module. This is a flight photo. The large box in the background is the pump module, and the FGB is the center part in the middle that has the grapple fixture for the station robotic arm. Once that's complete, Mike Fossum will relocate himself just behind the pump module. Together, the crew will lift up the pump module and present it to the station robotic arm. At that point, the robotic arm will grapple it and then maneuver it up to the external stowage platform, or ESP2, that was installed by STS-121 on one of their EVAs. This maneuver is expected to take around 30 minutes, so in order to save some time, we will be performing some activities in parallel. The first one is the relocation of the foot restraint from the port side of the ICC over to the starboard side in preparation for the TESS R&R. In addition, we will be removing a thermal blanket that is flown up around the new TESS, again in preparation for the swapping of the new and the old TESS. Once those activities are complete, the crew will translate up to the S0 truss structure. Again, in parallel with these activities, the station robotic arm will be being maneuvered by Lisa Nowak and Stephanie Wilson. So Mike Fossum and Pierce Sellers will be translating up to the station. They will split up, and Mike Fossum will work on configuring the old TUS for removal. As part of those activities, he will be releasing some bolts that restrain the TUS onto station, as well as disconnecting some electrical connectors from the station itself. And the flashing location is the location of the old TUS. At the same time, Pierce Sellers will be located just opposite of where he was for the beginning of EVA 1. This time he will be at the Nader IUA, which again is the interface umbilical assembly. This is the IUA that fired inadvertently back in December. And since it has fired, we actually have to do a full R&R. The blade blocker will not work for this one. So Piers will be taking the new one out to the work site, and he will be removing the old one and reinstalling the new one. And we'll get a close-up here of the area. Again, the flashing blue area is the IUA itself that will be removed. It's an interface with 4 bolts and 2 electrical connectors. Once that's complete, the station robotic arm should be waiting for us over at ESP2. The crew will translate out there. Pierce Sellers will ingress the foot restraint that you see down in the lower right-hand corner, and Mike Fossum will be behind the pup module again. This time they'll do just the opposite of what they did in the payload bay. They'll receive the pup module from the station robotic arm, and then they'll set it down onto ESP2 and secure it there. And again, this is the spare pup module, and that will be located there for any future flights that need it. Once that's complete, the station robotic arm is now available for the crew to get onto. So Mike Fossum will configure a foot restraint onto that station robotic arm end effector. He will ingress the foot restraint, and then together, Pierce Sellers and Mike Fossum will rotate the TUS out and physically remove the old TUS from the station truss structure. This is some footage again from the NBL during crew training. It gives you an example of how large the TUS is. The TUS weighs around 330 pounds. However, the center of gravity is right in the middle of it, so it's a very simple two-mass handle. Once it's removed, Mike Fossum will have the old TUS in his hands, riding the station robotic arm. He will be taken down to the payload bay. Again, this maneuver will take a little bit of time, so Pierce Sellers will actually translate down to the payload bay still first, and he will configure the old TUS for removal. Once down there, they'll be going through some choreography of the actual swap. This is Pierce Sellers in a foot restraint, and he has just been handed the old TUS by Mike Fossum. Mike will then maneuver over to the new TUS using the station robotic arm, and then the crew will do a swap of the new for old TUS. In the end, Mike Fossum on the station robotic arm will have the old TUS, and he will restow that onto the launch support equipment, getting it ready for coming home. Once that's complete, Pierce Sellers will finally hand the new TUS back to Mike Fossum, and Mike Fossum will ride the station robotic arm back up to the space station for installation of that hardware. Again, this will take a little bit of time. So during that time, Pierce Sellers will secure the old TUS onto the ICC to come home. Then he will meet up with Mike up at the space station. Together they will install and rotate the TUS down for its final installation. Once that's complete, basically the only thing left is the routing and securing of that TUS. And then the removal of the foot restraint from the station robotic arm. The crew will gather up their tools and accessories, and then translate back to the joint airlock for ingress. And that's the end of EVA 2. EVA 3 is currently an unscheduled EVA. As you heard throughout the day, depending on orbiter consumables, if we are able to perform this EVA, it will be on flight day 9. There are 2 major objectives for this EVA. The first one is an infrared camera DTO. This camera has 2 objectives within it. The first one is the imaging of some orbital wing leading edge RCC panels. This imaging is specifically only for data gathering, and that information will be brought back home for verification of some thermal analysis and thermal models. The second part of the IR camera DTO is for imaging of some samples within the payload bay. what we're going to look at is see whether or not the infrared camera can possibly see damage that's on the backside of some RCC. The rest of the the rest of the third EVA is an RCC DTO. We are flying some RCC samples within a TPS sample box, very similar to that of STS-114. The crew will be using the NOAX RCC repair material to enact some repairs, and that's basically the objectives for EVA 3. So at this point, if we can go ahead and roll the video for the third EVA, please. EVA 3 will start like the other EVAs. The crew will be egressing from the ISS joint airlock. This time, however, the station robotic arm will meet the crew right at the airlock. Their first task will be configuring the station robotic arm with a foot restraint, the one that you see flashing there. This will allow the crew to once again ride the station robotic arm down to the payload bay. Once that foot restraint is configured, Pierce Sellers will ingress the foot restraint. During that maneuver, Mike Fossum will translate down to the payload bay, and he will retrieve the second foot restraint along his translation path. During the maneuver, there will be a pause where Pierce Sellers on the station robotic arm will be using this infrared camera again to perform imaging of the wing leading edge of the orbiter. The crew will have a display that can show them what the infrared camera is seeing. The crew will just pick a couple of RCC panels, take some images. It's going to be a 20-second video. And then once that's complete, the maneuver will continue down to the payload bay for the rest of the EVA. Again, this maneuver will take a little bit of time, so Mike Fossum will translate down to the payload bay. He'll arrive before Pierce Sellers. The first thing that he's going to do is configure the foot restraint that you see in the aft portion on the orbiter payload bay sill there. This will be the foot restraint that he uses during the DTO itself. Once those activities are complete, he will open up the TPS sample box that's located on the aft part of the payload bay. This is the exact same design as was used on STS-114 for their TPS DTOs. However, the layout within the sample box is actually different than that from 114. This is a more detailed footage or video of how the samples will look within the TPS sample box. In the upper left-hand corner of the layout, there are two samples that actually have no damage on the forward part of the RCC itself. Some damage was created on the back side, and these two samples will be used for the infrared camera DTO. The way that the infrared camera works is that it measures thermal gradients across the RCC itself, and so by doing that, you can actually see damage that's located on the back side that's not visible to the naked eye. There are two what we're calling RCC pallets located in the center of the sample box, and then one located on the bottom left-hand corner of the sample box itself. During the repair activities, the crew will be using these pallets to help outgas any volatiles from the NOAX RCC repair material. So these pallets will be useful during the actual repair activities. In addition to those pallets, we have an additional 8 RCC specimens that we're hoping to repair by the end of the EVA. If we could continue with the rest of the video, please. These are the positions that the crew will be taking during the repair activities. Mike Fossum is on the right of your screen, and Pierce Sellers is again on the station robotic arm. This is footage of the crew practicing their choreography in the NBO. We can't actually extrude any material in the pool. However, there's a lot of choreography in work between the two crew members that needs to be practiced, and this is what they're doing in this video. This is footage similar to that you saw on STS-114's press briefing. This is the NOAX material being extruded in a human thermal vacuum chamber. This material is does behave differently in a vacuum. There are some volatiles within the material itself that come out of solution once exposed to vacuum. In order to enact a good repair, what we want to do is expose as much of the material as we can to this vacuum to make sure that those volatiles or possible bubbles and voids come out of the material. The material, once we find the sweet spot of the material, we then move the material from the pallet over to the repair itself to enact a good repair on the RCC samples. Those samples will be brought back home and tested in various ways. Some of it will be non-destructive testing and some of it will be in ArcJet testing. Once those samples are completed, the crew will begin their cleanup activities. The TPS sample box will be closed, and then actually Mike Fossum and Piers Sellers will swap locations. Mike will ride the station robotic arm back to the joint airlock, and Piers will translate back. Along the way, again, there will be a pause where Mike Fossum will use the infrared camera, similar to what Piers Sellers did on the way down. We'll again take a 20-second video footage of the orbiter wing leading edge, and then the crew will clean up the station robotic arm, ingress the joint airlock, and that will be the end of the VA3. That's actually all I have at this point.
Okay, so with that, we'll start with questions here at the Johnson Space Center. Please state your name and affiliation, and we'll start back here.
Mark Carruth from the Houston Chronicle. I'm wondering, during the first spacewalk, when they're doing the boom stability test, what was the thinking about not actually having them go under the orbiter on this test? And will that be something that might be incorporated into a future test of this nature on a flight down the line, or is that to be determined?
As far as a reach and access, we have performed several analyses that tell us what the different configurations are to make sure that we have good access to the various parts of the vehicle. Since this is the first time, we have various models that tell us how the boom will behave. However, at the same time, we don't want to put ourselves in a riskier position that is necessary. So we're going to go through several arm positions to give us a variety of different deflections, but we don't want to get underneath the vehicle where we get close to tile and possibly impart some damage that wasn't already there.
Alan Boyle with MSNBC. I wondered how much practice has been done for contingencies in case there is the sort of operation that was required during STS-114, removing gap fillers or even making repairs. Could you discuss how much that's been prepared for?
Sure. After Columbia, we've actually created around 15 additional classes that the crew takes to prepare for TPS inspection and repair capabilities. During STS-114, when the gap issue came up, gap filler situation came up, it was actually Piers Sellers and Mike Fossum, the two EV crew during this flight, that assisted with the development of the workarounds for those procedures. So they are very knowledgeable on any gap filler issues, along with the additional TPS classes. They're very confident in their capabilities for any contingencies.
I assume that if there was something like that that needed to be done, that would be during EVA3?
It will all depend on when we get the information, how much additional analysis will be required, and when the final decision is made, we will have to get some detailed procedures, get information to the crew. So it's possible that it will happen on EVA3. If it can happen earlier, then the earlier the better, so we get the results back.
Yeah, Jim O'Rourke with NBC. A couple things on other contingencies. One, of course, last EVA on a station they had a detached foot restraint that floated off. I'm not sure what direction it went off in, but apparently it was safe. What kind of procedures do you have in place for keeping things from not floating off? And secondly, I presume that they do have the helmet cams and safer for both crewmen, right?
That is correct. We are using safers for all three EVAs, and we will also have the helmet cameras, which will provide us some excellent shots, especially during the boom P2. I think it'll be very exciting. The standard, the very first rule of EVA is you always make a tether before you break a tether. That minimizes the risk and the possibility of losing any hardware. When you hand things back and forth between crew members or before you stow something, you want to make sure you double check, you install it, you do a pull test on it, and you secure it before you release your tether. So those are the standard procedures that we have in all EVA training.
Question back here.
One Larry, New York Times. That first EVA you mentioned, as they assemble the end of the platform and foot restraint, you have these 4 load cells. What are they? Are they accelerometers and multi-axis, or what are they? What do they tell you?
Unfortunately, I don't have the details of how the load cells are built. I can get that information for you, however, after the press briefing. What I do know is that there are 4, and we will be recording the inputs provided by the crew throughout the various activities throughout the entire DTO. That information will be recorded, brought back down to the ground, and we'll use it for post-flight analysis and verification of the models that we have. But I can definitely get with you and get you that information.
All right, we see there's 2 quick ones for me. That you said it was an 85-foot tether on the boom deflection DTO. Where is the tether attached?
Okay, we want to attach to rigid structure and structure that is secured, and we consider the boom a payload. So we don't want to secure the crew to the payload itself. We want to secure the crew to the shuttle robotic arm. So we do that. We attach our 85-foot safety tethers that we have to the end effector on the shuttle. There's a handrail there that has an attachment point, and the crew safety tether is attached there.
Yeah, just to make sure I heard you right. When you're out in positions 2 and 3, the max deflection you're talking about is 4 to 5 feet. You're expecting, is that right?
About 4 feet.
4 feet. Okay, thanks.
Chris Kreidler from Florida today. Could you talk about maybe the toughest task to learn from the astronaut's perspective when it comes to doing these spacewalks? What was most challenging in the training?
It's kind of hard to answer, but I think one of the major things, mostly for new crew members, are not really understanding what it's going to be like on orbit. All we can do is we have various simulators here. We have the NBL that gives them a feel for being as neutrally buoyant as they can be while doing the tasks. However, when they get on orbit, we have at the very beginning of an EVA, the first EVA of a crew member that has never performed an EVA before, there's a period where we actually give them about 5 or 10 minutes to adapt themselves. So they just do some body motions and rolls and stuff like that to make sure that they are comfortable with continuing the rest of the EVA. As far as the tasks themselves, the boom DTO was interesting to get ready for. It took a variety of different applications, various models, various analysis, from virtual reality, the 6 degree of freedom trainer that you saw. We had some analysis performed with the 3 degree of freedom trainer also. And so the crew could perform these part tasks, but putting it all together can only be done on orbit.
Todd Halverson of Florida today. I'm curious about the challenge of developing procedures for the truss reel assembly swap out, given the fact that you have what, 6 months to prepare for a fairly complex operation. And I'm also wondering what concerns you might have for the potential for structural failure at the OBSS-RMS connection point, if you will, during the DTO 849.
Okay. Onto your first one, with regards to procedures for the TUS R&R, as you mentioned, it was around December, actually right before Christmas, and I was on the phone and doing a lot of research. There are also several people in the EVA group that have a good understanding of several tasks. So we have a good database to go to. So I went to those people and got their knowledge before we could actually start developing procedures. Once that's complete, and that actually didn't take that long, then the lead item was actually making sure that we felt comfortable with the crew getting trained and prepared for the EVAs. The second part of your question was as far as structural. It's more of a robotics question, but analysis has been done to make sure that with all the boom deflections and inputs that we impart during the boom DTO, that it is a structural sound interface between the shuttle robotic arm and the boom.
Kelly Young with New Scientist. Could you describe why you're looking at damage to the backside of the RCC? What kind of scenario that damage could occur?
Okay. An example is we have wing leading edge sensors that can give us information on where possible impacts take place. However, if for some reason something were to happen, we are carrying EVA as an inspection capability, sometimes one fault deep and sometimes multiple failures deep. If we don't have the boom to perform inspections, we have a laser package failure or something like that, then EVA can go out and perform an inspection. The naked eye can't inspect down to the resolution that we would need to see. So therefore, if we know the general area of where an impact took place, if the infrared camera can actually provide us that information, then we have another source other than just the naked eye to verify how the damage is and where it was located.
Jim Over, two follow-ups here. First, a quick one: Who built the TUS? Was that the Canadian or the TUS structure? Pieces from where? Who built it?
I actually don't know that. I'll have to get back with you on that.
And secondly, you'd mentioned a familiarization adaptation for our new spacewalker. Raises the interesting question, and please talk to it. How much easier do you find it to be a trained and experienced spacewalker plus EVA for crewman for a new EVA? Is it significantly easier to train a person who's already done it in space, or is it about the same?
I think it's actually about the same. The procedures and the timelines and all those details are worked out using the training systems that we have here on the ground. However, the nice thing about having a previously flown crew member that's done EVAs like Pierre Sellers is that he can provide his knowledge base to assisting Mike Fossum or his EV2 in some possible different methods of actually doing something. There are always different ways to approach a task, and using his input and using the input from previously flown crew members that have done EVAs already, we can use that information not only for other crew members, but also for us to get a better understanding.
Okay, I understand there's a question at NASA headquarters, so we'll go to that next.
Yes, this is Seth Borenstein at AP. On the boom DTO, if that does, I know it's to verify that it's a suitable work place platform. If it is not, if you can't verify it, if it is not suitable, what's the most likely scenario that how it would be not suitable, and what would the crew have to do at the time? It's happening and you're finding it's not suitable. What would the crew end up doing at that time?
Okay. The way that we're going to verify whether it's a viable work platform is, again, threefold. We'll be taking some photogrammetric measurements and overlays on the orbiter windows. That'll give us just an example of what kind of deflections, a measurement of what kind of deflections we have. A lot of the information will also be subjective from the crew themselves. When we go to the port 1 truss element and the crew is imparting forces into that structure, we have some detailed actions that we have for them to perform, and they're going to be providing us feedback on whether or not they were able to accomplish those. An example that I've heard is basically you're painting a house and you're standing on a wobbly ladder. Are you able to, paint the entire side of the house, or can you do work so fine that you can actually do trimming, on the windows? So it's stuff like that that's subjective that we're going to get back. And I actually forgot the second half of your question.
If the crew, for example, using the painting the house analogy, if they find that this is too wobbly a ladder, what do you do at that time period? If during that point the crew says, this is from their what they're saying is this isn't working, what happens next?
Okay. We actually, as I mentioned earlier, have kind of a build-up approach. So the first thing we actually have to accomplish is just setting up the boom tip. We're going to install all the hardware on there, and then Peer Sellers is going to ingress. If we get to the first DTO position and the crew does not feel comfortable with this, we actually can do the exact same thing at the mid location on the boom itself. This would give us, instead of a 50-foot leverage arm, it's now a 25-foot, where the moment and the actions will be drastically reduced. And so that would be the next step that we would do, making sure that the 25-foot moment arm would then be a viable worksite platform. We would continue and perform the DTO exactly as written, and just go through the different motions and establishing whether or not we could do the DTO at the 50-foot mark or at the 25-foot mark, and we can actually reach the majority of the orbiter to perform TPS inspection repairs just from the halfway point on the boom. So we would actually not be losing that much capability if we would not be able to do it from the tip, but would be able to do it from the mid.
Okay, now we're back here at the Johnson Space Center for some follow-up.
Tracy Watson, USA Today. This first EVA you're doing is pretty novel, and I'm wondering what the EVA crew members have to take special care not to do, or what kinds of things they need to watch out for that maybe they've never had to be careful of on an EVA before.
I think that basically the crew is just going to be aware of their environment. I think it's a thing that we have to do with every EVA. But again, this is kind of a build-up approach. If the crew feels that doing a quick motion makes them uncomfortable, then we've now learned that they can't do a quick motion. Cannot. It's all in what feedback we get back from the crew. If they're comfortable doing quick motions, if they're comfortable doing moderate to aggressive laybacks, slower laybacks, reaches, and handing tools back and forth, a lot of these activities, again, are things that are expected that are going to be necessary for a TPS inspection repair. So a lot of it will be subjective for the crew to tell us whether or not they are comfortable. If we can actually perform the task that we've outlined for them, that's one objective. The other objective is, are they comfortable and could they repeat this task?
Bill Harwood again from CBS. And I know this is probably more of a program question. I know you guys obviously have to talk about this. Being able to use this as a work site obviously is important if you get something you've got to fix and you can't get to the station or something like that. But how important is this for a Hubble flight eventually?
That's a very good question. It all depends. Right now, actually, there is no Hubble flight on the manifest. As you know, it's all going to depend on the results of the overall flight, STS-121 in general, and how the flight objectives go. Apart from the boom itself, if we're not allowed, or if we cannot do a repair from the boom tip, possibly the boom midsection, as I mentioned earlier, we can reach the majority of the TPS repair area from the midsection. And it also depends on where the damage is located on the vehicle. If it's closer to the nose, we can actually reach the majority of that just with the shuttle robotic arm. No boom is necessary. If it's farther back in the vehicle, we actually may not have to impart any repair at all, because even if it trips the boundary layer, it doesn't cause any damage because there's nothing downstream to cause damage to. So I think it's all relative to the type of damage, where the damage is located, and whether or not we can actually reach it from the shuttle robotic arm.
Irene Fox with Reuters. I'm sorry if you might have mentioned this, but are the crew members going to be holding any actual plugs or tools or equipment that would be needed in a TPS repair during the test?
They will actually not be holding anything except for that force measurement device that you saw Mike Fossen holding in the video. We don't want to, we have a limited amount of hardware and we don't want to use that to practice. They know the motions that would be required and the amounts of forces that would be required to actually perform this repair. For example, at a tile repair or an RCC repair, the swiping motions, the pushing motions, they've all been trained well and they understand the load inputs and actually required. So in just using any tool, which in this case would be the force measurement device, it actually gives him some feedback to make sure that he's actually imparting enough force to mimic those repairs. So that's actually the only thing that's going to be in their hands.
Todd Halverson in Florida today again. With just a couple, you may or may not know this, I certainly don't, but why were the cable cutters designed into the TUS reel assembly to begin with? It sounds like you wish they weren't there now. And in terms of training for the DTO with the boom, do you actually have a mock-up of the OBSS and the RMS together in the NBL? And if so, I'm wondering if you've had any trouble with laybacks or quick motions in the pool environment.
Okay, the first part to your question with regards to the TUS itself, the blade cutting feature was actually added as a desired feature initially. We have two TUSs, one that's just located zenith and one just nadir of it on the S0 truss element. Again, these provide the power and data to the MT and the MBS as it translates between work sites. The way that the TUSs work is they reel out cable, as much cable as is necessary, and then as the mobile transporter moves back, it actually reels it back in. In order to have a safe system, the MT and the MBS have to be locked down at various work sites along that truss element. The concern was if during this translation period one of these cable reels were to jam, then it would actually prevent the motion to continue to a viable worksite platform, to a viable worksite where it can be locked down. So then that would give us the capability to actually send a command to cut it. We have a fully redundant system, so then we could continue at that point, lock it down, and have a safe system. The second question with regards to the boom training, in the NBL, we have a separate mock-up. We have just the boom itself and just the shuttle robotic arm. We actually cannot put those together because of 1G input loads into the mock-ups themselves. They wouldn't structurally be able to withstand that. So we had to train using various simulators. The boom tip setup that you saw in the video, that was trained using the boom mock-up. The laybacks and other activities that you saw Pierce Sellers performing, those were trained using the shuttle robotic arm. So using those various items, we were able to accomplish the full gambit of activities.
Are there any other follow-ups here at Johnson? Seeing none, I think that will conclude our spacewalk overview.